Look up at the night sky, past the familiar stars of our own Milky Way, and you will find a faint, wispy cloud, a ghostly smudge of light that has guided sailors and sparked imaginations for millennia. This is the Large Magellanic Cloud, our closest galactic neighbor, a satellite galaxy swirling in a slow, cosmic dance around our own. It feels distant, almost like a backdrop to our own galactic story. But what if that backdrop is hiding something profound? What if this seemingly quiet companion is actually a cosmic laboratory, buzzing with activity so strange and so bizarre that it fundamentally challenges the laws of physics as we know them? We have gazed at it for centuries, yet we are only just beginning to understand that the Large Magellanic Cloud is not a passive neighbor. It is a vault of cosmic secrets, each one more puzzling than the last. Today, we are embarking on a journey to unlock that vault. We will voyage 160,000 light-years to explore 30 of the most inexplicable phenomena ever discovered. We are talking about stars that vanish without a trace, celestial objects that pulse with rhythms we cannot decipher, and regions of space where the very fabric of reality seems to warp and bend. This is not just a catalogue of interesting facts. This is a descent into the deepest mysteries of our cosmic backyard. Each phenomenon we uncover will push the boundaries of what we believe is possible, forcing scientists to question long-held theories and consider possibilities that sound more like science fiction than astrophysics. This is a frontier where the rules are still being written, and what we find there might just redefine our place in the universe. So prepare to have your curiosity ignited and your sense of wonder expanded. This exploration is about more than just distant lights in the sky. It is about the human drive to understand the unknown, to look into the darkness and demand answers. The mysteries of the Large Magellanic Cloud are a testament to the fact that the universe is far stranger, far more dynamic, and infinitely more fascinating than we could ever imagine from our small corner of the Milky Way. Let's begin our countdown of 30 strange phenomena that prove our nearest galactic neighbor is the most enigmatic place we never knew was right next door. Our journey begins with an event that shook the astronomical world, an explosion so bright it could be seen with the naked eye from another galaxy. In February 1987, a star in the Tarantula Nebula of the Large Magellanic Cloud met its spectacular end. Supernova 1987 became the closest and brightest supernova witnessed in nearly 400 years, offering scientists an unprecedented front-row seat to the death of a star. For months, it outshone entire galaxies, and the data collected revolutionized our understanding of these cosmic cataclysms. But as the initial brilliance faded, it left behind a puzzle far more enduring and perplexing than the light show itself. At the heart of this expanding cloud of debris, astronomers expected to find a remnant. When a massive star collapses, the laws of physics dictate that its core should be crushed into an incredibly dense object, either a rapidly spinning neutron star or a black hole. For decades, every powerful telescope at our disposal, from the Hubble Space Telescope to the Chandra X-ray Observatory, has been trained on that exact spot, listening and looking for the telltale signatures of this newborn cosmic corpse. Yet, despite all our efforts, we have found nothing but an eerie silence. The compact object is missing. It's as if the star simply vanished, leaving behind only its glowing funeral shroud. Adding another layer to the mystery is the supernova's bizarre structure. Instead of a simple, spherical cloud, 1987 unveiled a stunning and unique arrangement of 3 glowing rings, a cosmic hourglass floating in space. This intricate shape suggests a history of complex stellar winds and interactions long before the explosion, a story we are still piecing together. The very nature of the explosion was also peculiar. It was weaker than standard models predicted for a star of its size, hinting that our textbooks on how stars die are still incomplete. The continued absence of the central remnant forces us to consider extraordinary possibilities. Perhaps the core collapsed directly into a black hole so young and quiet that it emits no detectable radiation. Or maybe it formed a neutron star shrouded by an impossibly thick veil of dust, hiding it from our view. Every year that passes without a discovery deepens the intrigue, making Supernova 1987 not just a relic of the past, but an active, unsolved case file in modern astrophysics. But if the lingering ghost of a dead star presents one kind of mystery, the vibrant, chaotic nursery of the Tarantula Nebula presents another entirely. Just a short cosmic distance from the site of Supernova 1987 lies a region of such sheer, raw power that it defies all local comparisons. Known officially as 30 Doradus, the Tarantula Nebula is not merely a star-forming region. It is the greatest stellar factory we have ever observed in our entire local group of galaxies. To grasp its scale, consider the most famous stellar nursery in our own Milky Way, the Orion Nebula. It is a beautiful and familiar sight, a celestial cradle that has inspired countless observers. Now, imagine an object so vast that if you were to replace the Orion Nebula with the Tarantula Nebula, positioning it at the same distance of about 1,300 light-years away, it would not just be a bright spot in the sky. It would span an area equivalent to 60 full moons, its glow so intense that it would cast discernible shadows on Earth at night, turning darkness into a perpetual, eerie twilight. This is the colossal nature of the phenomenon we are confronting. Within this sprawling cosmic cloud, star birth is not a gentle process, it is a violent, explosive affair. The nebula is a maelstrom of glowing gas and dust, illuminated from within by the fierce radiation of newly ignited stellar giants. At its very heart lies a spectacular cluster called R136, a dense metropolis of stars that contains some of the most massive and luminous suns ever catalogued. These are not the stable, long-lived stars like our own sun. They are stellar behemoths, monsters that burn through their nuclear fuel in just a few million years, living fast and dying young in spectacular supernova that will, in turn, seed the nebula with new elements and trigger further rounds of star birth. The energy pouring out of this central cluster is so immense that it sculpts the surrounding gas into fantastic pillars and bubbles, creating a landscape of cosmic violence and beauty. This ferocious activity has a startling side effect, the creation of runaway stars. Within the gravitational turmoil of the tarantula's dense clusters, stellar interactions can become incredibly violent. When two stars pass too close to one another, their gravitational dance can slingshot one of them away at an astonishing velocity, ejecting it from its birthplace like a stone from a catapult. Astronomers have tracked these fugitive stars racing away from the nebula at speeds exceeding hundreds of thousands of miles per hour, destined to wander alone through the interstellar void. The presence of these runaways is a direct testament to the incredible forces at play within the nebula, a natural consequence of packing so many young, massive stars into a relatively small volume of space. Yet the greatest puzzle of the Tarantula Nebula is not what is happening now, but why it is happening at all on such an unprecedented scale. What cosmic conditions conspired to create this epicenter of stellar genesis? The leading theory suggests it may be the result of a slow-motion chain reaction. The gravitational pull of the Large Magellanic Cloud itself, combined with the pressure from stellar winds and supernova shockwaves from earlier generations of stars, could have compressed the gas to a critical density, igniting this sustained frenzy of creation. It's a self-perpetuating cycle where the death of stars fuels the birth of new ones. However, some scientists wonder if a more dramatic event was the initial spark, such as a close encounter with the small Magellanic Cloud or even a direct collision between massive gas clouds millions of years ago. The Tarantula Nebula, therefore, stands as a living laboratory, offering us a glimpse into the conditions that likely prevailed in the early universe when the first grand clusters of stars were forged. It challenges our understanding of how such extreme environments arise and what their ultimate legacy will be for the evolution of their host galaxy. While the Tarantula Nebula dazzles with its brilliant light, the next great mystery of the Large Magellanic Cloud is defined by an absence of light altogether. We now turn from what we can see to what we must infer, confronting the ghostly presence that may, in fact, be the most significant component of the entire galaxy, its vast, invisible halo of dark matter. This is not a cloud of dust or a void in space. It is a colossal sphere of an unknown substance that envelops the visible galaxy, a hidden giant whose gravitational pull is the only way we can detect it. The very existence of this halo is central to understanding how the Large Magellanic Cloud holds itself together, and more remarkably, how it is actively reshaping our own Milky Way from the outside in. The evidence for this dark matter halo comes from a fundamental discrepancy between what we see and what we measure. When astronomers calculate the mass of the Large Magellanic Cloud by adding up all its stars, gas, and dust, the total is simply not enough to account for the speeds at which stars and gas clouds orbit the galaxy's center. According to the laws of gravity, a galaxy with only the mass we can see should not have a strong enough gravitational grip to prevent its outer regions from flying apart. The stars are moving too fast for the visible matter alone to hold them in orbit. The only logical conclusion is that there must be an enormous amount of additional mass that we cannot see, a gravitational anchor providing the extra pull needed to keep the galaxy intact. This invisible mass is what we call dark matter, and it is thought to form a vast, diffuse sphere that extends far beyond the galaxy's luminous disk. But the story becomes even more fascinating when we consider the interaction between this invisible giant and our own galaxy. The Milky Way is also swaddled in its own immense dark matter halo. As the Large Magellanic Cloud swings around our galaxy on its billion-year orbit, these two immense halos of dark matter are not simply passing through each other harmlessly. Instead, they are interacting gravitationally in a complex cosmic dance. Recent sophisticated computer simulations suggest that the dark matter halo of the Large Magellanic Cloud is dense and massive enough to actually gravitationally tug on the Milky Way's halo as it passes. This interaction is not unlike a large ship moving through water, creating a wake behind it. Astronomers believe they have now detected this very wake. By meticulously mapping the motions of stars in the outermost fringes of the Milky Way, a region known as the stellar halo, scientists have found a distinct ripple-like distortion. The pattern of these stellar motions is not smooth and symmetrical as would be expected from a tranquil, isolated galaxy. Instead, it shows a telltale disturbance, a collective sway that aligns perfectly with the predicted path of the Large Magellanic Cloud's dark matter halo as it plows through our own. This provides some of the most compelling indirect evidence yet for the presence of dark matter around our satellite galaxy. It demonstrates that the Large Magellanic Cloud is not a passive bystander. It is an active participant, its unseen mass dynamically influencing the architecture of its much larger host. This discovery opens a new window into one of the greatest puzzles in modern cosmology, the true nature of dark matter itself. By studying how the dark matter halo of the Large Magellanic Cloud behaves, how it interacts, how it is possibly stripped away by the Milky Way's gravity, and how it distorts our galaxy, scientists can test theories about what this mysterious substance actually is. Is it a sea of exotic, yet-to-be-discovered particles, or does it point to a need to revise our understanding of gravity itself? The invisible giant encircling the Large Magellanic Cloud is therefore more than just a solution to a local gravitational mystery. It is a key piece in the quest to understand the fundamental fabric of the entire universe. Moving from the invisible gravitational grip of dark matter, we encounter a theory so dramatic it sounds like the plot of a science fiction epic. the possibility that a supermassive black hole was violently evicted from its throne and is now a fugitive roaming the depths of the Large Magellanic Cloud. We are accustomed to thinking of supermassive black holes as the sedentary anchors of galaxies, the inevitable behemoth sitting at the very center, governing the orbits of billions of stars. But what happens when the king is dethroned? The very structure of the Large Magellanic Cloud suggests that this cosmic coup may have already taken place. The first clue lies in what appears to be a conspicuous absence. Unlike most galaxies of comparable size, the Large Magellanic Cloud does not have a clearly defined, massive central black hole. Our own Milky Way has Sagittarius, a star, a giant weighing 4 million times the mass of our Sun. Yet, searches for a similar central engine in the LMC have come up surprisingly empty. This missing monarch is, in itself, a puzzle, but the plot thickens when we examine the motions of stars and gas clouds within the galaxy. Astronomers have detected strange, swirling patterns and peculiar velocities that are difficult to explain through the gravitational influence of visible matter alone. There are streams of stars moving in concert, as if they were all tugged by a single, powerful, and invisible force passing through their midst. It's as if the ghost of a gravitational giant is still haunting the galaxy, its past presence imprinted on the motions of the stars it left behind. The most compelling explanation for these anomalies is a past galactic merger. The Large Magellanic Cloud, like all galaxies, has a history of collisions and acquisitions. Billions of years ago, it may have consumed a smaller companion galaxy. When two galaxies merge, their central black holes are drawn toward the new common center of gravity. They begin a slow, spiraling dance, eventually coming so close that they form a binary pair. According to Einstein's theory of general relativity, such a pair loses energy by emitting ripples in spacetime known as gravitational waves. If the two black holes are of uneven mass, the emission of these waves can be lopsided. When they finally coalesce, the resulting single black hole can receive a powerful kick, a recoil so violent that it can be ejected from the galactic center entirely, sent flying into the interstellar wilderness at speeds of thousands of kilometers per second. This theoretical process provides a perfect mechanism for how a supermassive black hole could become a runaway. The implications of such a rogue black hole wandering through the LMC are profound. Its journey would be anything but quiet. As it plows through clouds of gas and dust, its immense gravity would compress the material in front of it, potentially triggering sudden and intense bursts of star formation in its wake, leaving a trail of young, blue stars like breadcrumbs across the galaxy. Alternatively, if gas were to fall directly onto the black hole itself, it could light up as a brilliant, moving quasar, a beacon that would drift unpredictably through the galactic disk, not anchored to any particular cluster or nebula. Detecting this lone wanderer, however, is a monumental challenge. Without a steady supply of accreted material, it would be dark and virtually invisible against the blackness of space. Its primary signature would remain its gravitational influence on the surrounding stars, a subtle tug that requires exquisitely precise measurements to confirm. Finding this cosmic fugitive would revolutionize our understanding of galaxy evolution. It would provide the first concrete evidence that the supermassive black hole recoil process is not just a theoretical curiosity, but a real, observable phenomenon that shapes galaxies. It would demonstrate that the central engine of a galaxy is not always a permanent fixture. It can be removed, fundamentally altering the galaxy's future development. The hunt for this missing black hole is therefore more than a celestial treasure hunt. It is a direct test of our models about the most violent and formative events in the life of a galaxy. The silence at the heart of the Large Magellanic Cloud may not be an emptiness at all, but the echo of a dramatic escape. Yet the idea of a runaway supermassive black hole is for now a compelling theory built on gravitational whispers. To find a confirmed black hole, we must turn our attention to a place where the evidence is written in blazing X-rays, a place of relentless and violent consumption. This brings us to one of the most intense and puzzling energy sources in the entire galaxy, a binary system known as LMC-X3. Here, in a gruesome celestial dance, a visible star is locked in orbit with an invisible monster, its outer layers being steadily stripped away and devoured. While we know this is a scene of cosmic predation, the true identity of the predator remains shrouded in mystery, its nature defying simple classification. The basic setup of LMC-X3 is both terrifying and elegant. A hot blue star, several times more massive than our Sun, circles an unseen companion in a tight orbit that takes just over 1.5 days to complete. The proximity is key to the violence. The gravitational pull of the unseen object is so powerful that it stretches the star into an egg-like shape, siphoning a continuous stream of stellar material from its surface. This gas doesn't fall directly onto the hidden object. Instead, it spirals inward, forming a superheated disk of plasma that rotates at a significant fraction of the speed of light. It is within this accretion disk that the drama unfolds. The gas particles, compressed and heated to temperatures of millions of degrees, release a torrent of high-energy radiation, primarily in the form of X-rays. This is the beacon we detect across the vast intergalactic distance, a scream of energy from a star being eaten alive. For decades, astronomers have classified LMC-X3 as a stellar mass black hole candidate. By measuring the orbital velocity of the visible star and applying Kepler's laws of motion, they can calculate the mass of the object pulling on it. The result is staggering. The unseen companion weighs in at approximately 7 times the mass of our Sun. This places it firmly in the so-called mass gap, a puzzling zone between the known populations of neutron stars, which typically max out around 2 or 3 solar masses, and black holes, which are usually found starting at around 5 solar masses. An object of 7 solar masses is too heavy to be a neutron star, as the degeneracy pressure that supports a neutron star against its own gravity would fail at that mass, causing a collapse. Therefore, the logical conclusion is a black hole. But LMC-X3 is no ordinary stellar mass black hole. Its behavior is what makes it a persistent enigma. What truly sets LMC-X3 apart is its incredible stability and sheer power output. Unlike many other X-ray binary systems, which flicker and flare unpredictably, LMC-X3 has been a remarkably steady and luminous source for the entire duration of our observation. It is one of the brightest persistent X-ray sources known in the local group of galaxies. This consistent brightness suggests that the accretion disk is stable and the flow of material from the donor star is unusually smooth and constant. The system seems to be in a perfect, albeit destructive, equilibrium. This relentless energy output pushes the limits of what standard models predict for a black hole of its proposed mass. The efficiency with which it converts infalling mass into energetic radiation is exceptionally high, leading some scientists to question if the compact object might be even more massive than initial measurements suggest, or if there is something unique about its spin or magnetic environment that amplifies its power. This unusual behavior opens the door to more exotic possibilities. Could the compact object in LMC-X3 be something rarer than a standard black hole? One tantalizing, though speculative, theory is that it could be a low-mass quark star. A quark star is a hypothetical celestial object that represents a state of matter even more extreme than a neutron star. In a neutron star, protons and electrons are crushed together to form neutrons. Under even greater pressure, these neutrons themselves might break down into their constituent parts, a soup of free quarks. An object like this could, in theory, support a higher mass than a neutron star before collapsing into a black hole, potentially explaining the mass gap object we see in LMC-X3. The emission properties of such an exotic star would be different from a black hole's, which might account for the system's peculiar X-ray signature and stability. While there is no confirmed discovery of a quark star, LMC X3 remains a prime candidate where such an object could be hiding in plain sight. The enduring mystery of LMC X3 underscores a fundamental challenge in modern astronomy. We are often forced to characterize these dark objects indirectly by observing how they influence their environment. We see the glowing accretion disk and the distorted star, but the central engine itself remains invisible. Every new observation with advanced telescopes like the Chandra X-ray Observatory or the James Webb Space Telescope provides more data, refining our models. Yet, LMC X3 continues to resist being neatly pigeonholed. It serves as a critical natural laboratory for studying the physics of extreme gravity and accretion processes, forcing us to question and refine our definitions of what constitutes a black hole and what other bizarre forms of matter might exist in the dark corners of the universe. Its steady, brilliant glow is not just a beacon of destruction, but a persistent question mark, challenging us to look deeper. While the brilliant X-ray scream of LMC X3 represents a black hole's present-day feast, our next mystery forces us to listen for much older, far quieter echoes. Scattered across the Large Magellanic Cloud are the ghostly remains of stellar cataclysms that unfolded not centuries but millions of years in the past. These are the ancient supernova remnants, vast and faint shells of gas expanding silently into the darkness. To the unaided eye, or even through a small telescope, they are invisible, their light spread so thin that it is overwhelmed by the glow of younger stars and nebulae. But with sensitive instruments that can capture specific wavelengths of light, these remnants reveal themselves as colossal, intricate structures, some spanning hundreds of light years. They are the fading fossils of the galaxy's violent history, and each one tells a story of a star's final, explosive act. Studying these ancient shells is like being a cosmic archaeologist. By analyzing their size, shape, and composition, astronomers can piece together the history of star formation and death throughout the LMC. The very existence of so many large, old remnants indicates that this galaxy experienced intense periods of stellar birth long ago, creating generations of massive stars that lived fast and died young. The gas within these shells is particularly telling. It is enriched with heavy elements forged in the heart of the progenitor star, and during the supernova explosion itself elements like oxygen, silicon, and iron. As these remnants expand and eventually disperse, they seed the surrounding interstellar medium with these crucial ingredients for future generations of stars, planets, and even life. By mapping the distribution and abundance of these elements, scientists can trace the chemical evolution of the entire galaxy, understanding how it became the element-rich environment we see today. Yet, the most intriguing aspect of these ghostly shells is not just their existence, but their bewildering variety of shapes. The classic textbook image of a supernova remnant is a perfect spherical bubble, like a smoke ring blown into space. This is what we would expect from a single, symmetrical explosion in a relatively uniform region of space. And indeed, some remnants in the LMC, such as the beautifully named DML-71, exhibit this near-perfect spherical form. This simplicity, however, is the exception rather than the rule. Many other remnants are wildly distorted, presenting themselves as fractured, lopsided, or even jagged rings. They look less like orderly bubbles and more like shattered glass frozen in the act of expansion. This is where the true mystery lies, because the shape of a remnant is not just a record of the explosion. It is a detailed map of the environment it exploded into. A perfectly spherical shell suggests that the dying star was a loner, erupting in a quiet, empty region of space where the interstellar medium was smooth and unchallenging. The blast wave could expand outward evenly in all directions, creating a cosmic bubble. But a distorted shell tells a far more dramatic story. The asymmetries and breaks are scars from a violent journey. They indicate that the supernova blast wave encountered a turbulent and uneven landscape. It might have slammed into dense, pre-existing clouds of gas and dust, which act like celestial obstacles, slowing the expansion in some areas while allowing it to race forward in others. The result is a remnant that is pushed and pulled into an irregular form. In other cases, the shape may be influenced by the star itself. If the progenitor star had a fierce stellar wind that carved out a cavity around it before it died, the supernova explosion would then interact with the complex walls of that cavity, leading to a more structured and less spherical remnant. Some of the most bizarre shapes even hint at multiple, overlapping cataclysms. In dense stellar nurseries, it is possible for massive stars to be born and die in quick succession. The remnant from one supernova might still be expanding when a nearby sister star explodes. The blast wave from the second explosion would then collide with the shell of the first, creating a tangled, interconnected web of gas that challenges astronomers to untangle the timeline of death. By carefully studying the intricate folds and filaments of these ancient remnants, scientists are essentially reading the weather report for the interstellar medium of the LMC from millions of years ago. They are learning about the density, the pressure, and the turbulence that shaped these cosmic graves, providing a deeper understanding of the dynamic ecosystem in which stars live and die. These faint, ghostly shells are therefore not just silent relics. They are active history books, their pages written in gas and their chapters defined by violence. But if the fossilized shells of supernova remnants tell a story of stellar deaths long past, the very structure of the Large Magellanic Cloud itself holds evidence of a trauma on an even grander scale, a galactic wound that has yet to fully heal. This brings us to one of the most profound architectural mysteries of the galaxy, the curious case of its counter-rotating core. Imagine a vast whirlpool of stars and gas spinning smoothly in one direction. Now picture that at the very heart of this whirlpool, the central region is slowly, stubbornly spinning the opposite way. This isn't a flaw in the cosmic machinery. It is a scar, a lasting signature of a violent event that fundamentally reshaped the galaxy billions of years ago. The discovery of this potential counter-rotation came from a painstaking astronomical detective effort. Measuring the rotation of an entire galaxy is not as simple as watching it spin. The timescales are far too long for any noticeable change within a human lifetime. Instead, astronomers use the Doppler effect, the same principle that causes a siren's pitch to change as it passes by. By carefully analyzing the light from thousands of individual stars in different parts of the LMC, scientists can determine whether those stars are moving toward us or away from us. When they map these velocities across the galaxy's disk, a clear pattern typically emerges. One side appears blue-shifted, moving toward us, while the opposite side is red-shifted, moving away, revealing the overall direction and speed of rotation. But when researchers focused on the motions of stars specifically in the central, bar-like structure of the LMC, the data revealed something startling. The pattern suggested that this dense central region might be rotating in the opposite direction to the outer disk of stars and gas. It's as if the galaxy's heart is beating to a different rhythm than the rest of its body. The most widely accepted explanation for this bizarre internal conflict is a dramatic galactic merger. The theory posits that billions of years in the past, the Large Magellanic Cloud cannibalized a smaller companion galaxy. This would not have been a gentle coalescence, but a violent, chaotic process lasting hundreds of millions of years. As the smaller galaxy was pulled in, its orbit would have decayed, and its stars would have been stripped away and assimilated into the larger LMC. However, if the victim galaxy approached from a particular angle specifically on a retrograde orbit, meaning it was orbiting in the opposite direction to the LMC's own spin, the aftermath would have left a distinct imprint. The stars from the devoured galaxy, with their contradictory momentum, would have settled preferentially into the central regions, creating a core that retains the memory of its backward motion. This is the galactic equivalent of stirring a cup of coffee one way and then dropping in an ice cube that was spinning in the opposite direction. The resulting swirls and countercurrents would persist long after the ice has melted. This theory, while elegant, is not without its challenges, which is why this phenomenon remains an active and heated topic of debate. Some astronomers propose alternative mechanisms that could create a similar observational signature without requiring a full-blown merger. One possibility involves intense and sustained bursts of star formation. If new stars were born in a powerful, asymmetric wave within the central bar, their collective motion and the pressure from their stellar winds could potentially disturb the inner dynamics of the galaxy in a way that mimics counter-rotation. Another, more complex idea suggests that interactions with the Milky Way's immense gravitational field could have torqued the inner disk of the LMC over time, slowly twisting it into a different rotational alignment than the outer disk. Resolving this debate requires ever more precise data. New missions like the European Space Agency's Gaia spacecraft are revolutionizing this field by providing exquisitely detailed measurements of the proper motions, the actual tiny angular movements across our sky of millions of individual stars within the LMC. By combining this data with spectroscopic velocity measurements, astronomers are building a three-dimensional map of how stars are moving throughout the galaxy. This will allow them to distinguish between a true, deeply embedded counter-rotating core and more superficial dynamical disturbances. The implications of confirming a past merger are enormous. It would mean the LMC is not a pristine, simple dwarf galaxy, but a hybrid, a product of a violent union that altered its structure, its stellar populations, and likely even triggered intense periods of star formation. This single, strange rotational anomaly is therefore a key to unlocking the deepest history of our closest galactic neighbor, a history written not in light but in the silent, opposing motions of its stars. Yet this architectural oddity of a counter-rotating core speaks to the grand gravitational history of the galaxy. But some of the most telling mysteries are written not in the motion of billions of stars, but in the bizarre behavior of individual suns. To find one of the most puzzling examples, we must journey into the ancient stellar cities of the Large Magellanic Cloud, its magnificent globular clusters. These are dense spheres of hundreds of thousands of stars, all bound together by gravity, relics from the very early days of the galaxy's formation. In these clusters, the stars are all primordial siblings, born from the same cloud of gas at roughly the same time, billions of years ago. This shared birth date is a fundamental rule for understanding them. The stars within a single cluster should all be the same age, and since the life of a star is determined by its mass, with heavier stars burning brightly and dying young, while lighter stars simmer for eons, the stellar population of an old cluster should be predictable. After billions of years, all the massive, hot, blue stars should have long since expired in spectacular supernova, leaving behind only the cooler, older, redder stars. The cluster should glow with a consistent, elderly red hue, which is why the discovery of blue stragglers was so profoundly unsettling. Scattered within these ancient red crowds, astronomers found stars that break all the rules. They are stars that appear paradoxically young, hot, blue, and massive, shining with a vibrant energy that simply should not exist in such an old environment. It is as if you walked into a retirement home and found a group of energetic teenagers living among the residents. These blue stragglers are not just a minor anomaly, they are a direct challenge to our models of stellar evolution, and the dense clusters of the LMC provide a perfect laboratory to study them. Their very existence forces us to ask a radical question. Can stars, under the right conditions, actually find a fountain of youth? The leading theories to explain these celestial anomalies are as dramatic as the stars themselves, and they both stem from the incredibly crowded conditions within a globular cluster. In these dense environments, stars are not isolated beacons as they often are in the galactic disk. They are packed together so tightly that the space between them is vastly reduced compared to our own neighborhood. In such a stellar metropolis, close encounters and even direct collisions are not just possible, they are inevitable over billions of years. The first theory, stellar collisions, is a scenario of cosmic violence. Imagine two older, sun-like stars, each plodding along on their own separate paths on a slow-motion collision course dictated by gravity. When they finally meet, they don't necessarily explode. Instead, they can merge into a single new star. This newly formed star would be composed of the combined hydrogen fuel from both its progenitors. With a fresh supply of fuel and a greater mass, this merged star would reignite its nuclear fires with a new intensity, heating up and becoming bluer, effectively reset its evolutionary clock. It would stand out brilliantly against the backdrop of its aging, redder siblings. The second major theory involves a slower, more insidious process, but one that is equally transformative. Many stars in the universe are born in binary systems, two stars locked in a mutual orbit. In a globular cluster, these binary pairs are common. The theory of mass transfer suggests that if the two stars are close enough, and one of them begins to swell into a red giant as it ages, its outer atmosphere can be gravitationally stripped away by its companion. This stream of hydrogen gas flows from the donor star onto the surface of the smaller, denser companion star. The recipient star, often a white dwarf, gains a new layer of hydrogen fuel. This fresh fuel can then ignite in a shell around the star, causing it to heat up dramatically, bloat in size, and become a blue giant. In this scenario, the star isn't truly young. It's an old star that has been artificially rejuvenated, its appearance radically altered by a cosmic blood transfusion from its partner. Studying blue stragglers in the LMC is particularly valuable because its clusters are different from those in our own Milky Way. They are often younger and contain more gas and dust, providing a different set of conditions to test these theories. By analyzing the light from these stars, astronomers can look for chemical signatures that betray their origin. A star formed from a collision might show unusual mixing of elements from the deep interiors of its parent stars. A star that has gained mass from a companion might show different atmospheric properties. Each blue straggler tells a story, and by reading these stories, we learn that stellar evolution is not always a solitary, predictable journey. In the crowded downtown cores of globular clusters, stars can interact, merge, and steal from one another, creating outcomes that would be impossible in isolation. They are living proof that in the dense heart of a stellar city, the rules of life and death can be rewritten. But the internal dynamics of stars and clusters are not the only forces shaping this galaxy. When we pull back to view the Large Magellanic Cloud in its entirety, its very architecture reveals a colossal imperfection, a fundamental asymmetry that sets it apart from most other galaxies of its kind. This is the mystery of its off-center, warped bar. Spiral galaxies, including our own Milky Way, often feature a central bar, a dense, elongated structure of stars that cuts through the galactic core. Typically, these bars are relatively straight and symmetrical, acting as a stable gravitational anchor around which the rest of the galaxy rotates. The bar in the Large Magellanic Cloud, however, is different. It is not a pristine, geometric shape at the heart of the galaxy. Instead, it is noticeably skewed, twisted, and most strikingly, it is not aligned with the galaxy's center of mass. It's as if the galaxy's backbone has been bent. This distortion is not a minor curiosity. It is a dominant feature that influences the entire galaxy's behavior. The bar is the most prominent stellar component of the LMC, containing a significant fraction of its older stars. Because it is so massive, its gravitational pull orchestrates the motion of gas clouds and guides the formation of new stars throughout the galactic disk. A symmetrical bar would create a predictable, orderly flow, but a warped, off-center bar creates a gravitational landscape that is uneven and chaotic. Imagine stirring a pot of water with a perfectly straight spoon. You create a smooth, rotating vortex. Now try stirring it with a bent, crooked spoon. The resulting currents would be turbulent and unpredictable. This is precisely the effect the LMC's bar has on its internal dynamics, leading to unusual patterns of star formation and gas flow that deviate from what we see in more isolated, symmetrical galaxies. So what colossal force could warp something as massive as a galactic bar? The prime suspect is a relentless gravitational influence from right next door, our own Milky Way galaxy. The LMC is not an independent island universe. It is a satellite gravitationally bound to a much larger host. As it travels on its long orbit around the Milky Way, which takes over 1 billion years to complete, it experiences immense tidal forces. These are the same forces that the Moon exerts on Earth's oceans to create tides, but scaled up to a galactic level. The side of the LMC closer to the Milky Way feels a stronger gravitational pull than the side farther away. This difference in force, this tidal pull, stretches and distorts the entire galaxy. It is this continuous cosmic tug of war that is thought to have pulled the bar out of its natural alignment, twisting it over millions of years. The galaxy is not simply rotating peacefully, it is being actively molded and deformed by its interaction with its giant neighbor. This tidal interaction also provides a compelling explanation for the bar's off-center position. Some sophisticated computer simulations suggest that as the LMC orbits the Milky Way, the tidal forces not only warp the bar but can actually shift the entire disk of stars relative to the more extended dark matter halo that surrounds the galaxy. The visible stars and gas feel the direct tidal pull, causing them to slide and shift, while the invisible dark matter halo, which makes up the majority of the galaxy's mass, remains more stable. This would make the bright, stellar bar appear offset from the true gravitational center of the galaxy defined by the dark matter. The asymmetry we see is therefore a direct snapshot of the LMC in a state of dynamic imbalance caught in the act of being reshaped. The consequences of this distorted core are far-reaching. The warped bar acts like a chaotic pump, driving gas flows in strange and unpredictable ways. This can lead to bursts of star formation in unexpected places, creating pockets of young stars far from the traditional spiral arms. It also helps explain why the LMC has such a large, single spiral arm on one side, a feature that gives it an irregular, lopsided appearance compared to the grand design spirals like the Milky Way. The gravitational turmoil generated by the bent bar prevents the galaxy from settling into a symmetrical equilibrium state. In a very real sense, the off-kilter bar is the engine of the LMC's continued evolution and its unique identity. It is a brilliant demonstration that galaxies are not static islands, but dynamic entities whose forms are constantly being sculpted by their interactions with the cosmic environment around them. While the warped bar demonstrates the galaxy's large-scale gravitational struggles, the interstellar medium within the Large Magellanic Cloud tells a story of a different kind of violence, not of slow tidal pulls, but of sudden, explosive energy on a truly colossal scale. This brings us to our 10th phenomenon, the enigmatic structures known as superbubbles. If you could see the galaxy in the kind of X-ray vision that reveals the distribution of hot gas, you wouldn't see a smooth, homogeneous cloud. Instead, you would see a landscape pockmarked with gigantic, hollowed-out cavities, some spanning hundreds of light-years across. These are not empty voids, they are cosmic bubbles blown in the thin fabric of the interstellar medium, and their existence points to a history of sustained, ferocious power emanating from the galaxy's most massive stars. To understand the sheer force required to create these structures, consider the energy involved. A single supernova explosion unleashes as much energy as our Sun will produce over its entire 10 billion-year lifetime. Now, imagine not one, but dozens of these cataclysmic events occurring in the same general region over a span of a few million years. Add to that the relentless hurricane-force winds pouring off the most massive stars throughout their short lives, which can blow with speeds of millions of miles per hour. This combination acts like a cosmic jackhammer, relentlessly pounding and pushing the surrounding gas outward. The collective effect scoops out a vast chamber of hot, low-density gas surrounded by a dense, expanding shell of compressed material. This shell is the bubble's visible edge, a glowing wall of energized gas that delineates the sphere of influence carved out by the stellar violence within. The superbubble known as N44 is a perfect and stunning example of this process, and it presents a fascinating twist. Located in the LMC, N44 is not a simple, single bubble. When viewed in detail, it reveals a complex, nested structure, a smaller, brilliant bubble nestled inside a much larger, fainter one. This is like a Russian doll carved out of interstellar gas. Astronomers believe this intricate shape tells a specific story about the life and death of stars in this region. The sequence likely began when the first generation of massive stars in the area blew a large cavity with their powerful winds. Then, these stars began to die in supernova explosions, further expanding the bubble. But the story didn't end there. The shock wave from this activity compressed the gas along the edge of the first bubble, triggering the collapse of dense pockets and igniting the birth of a second generation of stars. These new stars, born in the shell of the old bubble, then began their own cycle of fierce winds and eventual supernova, blowing the smaller, inner bubble from within the larger one. N44 is therefore a snapshot of sequential star formation, a celestial chronicle where the death of one stellar family directly leads to the birth of the next. The impact of these superbubbles extends far beyond their immediate vicinity. They are primary architects of galactic ecology. As a superbubble expands, it doesn't just move gas aside, it fundamentally transforms it. The shockwaves heat the interstellar medium to extreme temperatures, creating vast regions of million-degree gas that glow in X-rays. These shocks also accelerate particles to near-light speeds, creating cosmic rays that permeate the galaxy. Most significantly, the expanding shell sweeps up an enormous amount of material, much like a snowplow gathers snow. This can gather enough gas to reach a critical density, causing it to fragment under its own gravity and collapse into new stars. This process, known as triggered star formation, means that superbubbles don't just mark sites of past destruction. They are actively sowing the seeds for future stellar generations. They are a fundamental mechanism for regulating the pace of star birth across a galaxy, creating a self-perpetuating cycle of death and rebirth on an epic scale. However, the evolution of these structures holds persistent puzzles. Computer simulations of superbubbles often struggle to perfectly match the observed shapes and sizes of real-life examples like N44. The models suggest that bubbles should expand in a more uniform, spherical manner, but many observed bubbles are irregular and fractured. This discrepancy points to our incomplete understanding of the conditions within the interstellar medium. The reality is that the gas and dust between stars are not smooth. They are clumpy and turbulent, filled with pre-existing density variations. A superbubble's expansion will be dramatically altered as it encounters these invisible obstacles, bursting through thin regions and stalling against dense clouds. Furthermore, the energy input from the stars might not be as continuous as models assume. If there is a lull between supernova, the bubble might begin to cool and collapse inward before being re-energized by the next explosion. Studying superbubbles in the LMC, where we can measure distances and energies with great accuracy, provides the crucial data needed to refine our models. These gigantic cavities are more than just beautiful cosmic fossils. They are active experiments in astrophysics, challenging us to understand the complex feedback loop between the lives of stars and the galaxy they call home. While the violent, large-scale architecture of superbubbles is shaped by the collective fury of many stars, the final, more intimate death of a single, sun-like star creates a different kind of cosmic artwork altogether. These are the planetary nebulae, and within the Large Magellanic Cloud, they appear in a gallery of forms so strange and beautiful that they challenge our very understanding of stellar finales. Unlike the chaotic blast wave of a supernova, a planetary nebula is a star's last gentle sigh. In its final stages, a medium-mass star puffs off its outer layers into space, creating a glowing shell of gas lit from within by the star's hot, exposed core. From our vantage point, the LMC offers a unique curatorial advantage for studying these objects. They are all essentially hanging on the same wall. Because they reside in a galaxy that is a single, coherent structure, they are all at approximately the same distance from us, 160,000 light-years. This eliminates the guesswork involved in studying planetary nebulae within our own Milky Way, where determining whether a nebula is small and close by or large and far away is a major complication. The LMC provides a perfectly controlled laboratory, allowing astronomers to compare these celestial artworks directly and understand what truly causes their incredible diversity. If you were to browse this galactic gallery, you would quickly see that the simple, spherical bubble is merely a common theme, not the rule. Many of these nebulae exhibit astonishing complexity. There are nebulae with intricate bipolar lobes that stretch out like butterfly wings, others with bizarre, pinched wastes that give them an hourglass shape, and some, like the magnificent Southern Crab Nebula, that present a structure so unique it seems almost artificial. The Southern Crab, officially known as Hen 2149, does not look like its namesake crustacean from our world. Instead, it resembles a vast cosmic contraption, a central band of glowing material from which two pairs of opposing lobes erupt, one set much larger than the other. It looks less like a random explosion and more like a piece of intricate machinery, a celestial engine whose purpose we are only beginning to decipher. This level of intricate symmetry points to a powerful, focused process at work, something far more controlled than a simple, isotropic belch of gas. The prevailing mystery is how a spherical star can produce such wildly asymmetric structures in its death throes. The answer appears to lie not in the star's final act alone, but in the influence of an unseen companion. The leading theory for the formation of bipolar nebulae like the Southern Crab involves a binary star system. In this scenario, the dying star swells into a red giant, but its expansion is not free and unimpeded. It is gravitationally bound to a smaller, denser companion star, often a white dwarf. As the giant star sheds its outer layers, the companion star orbits within this expanding envelope of gas. Its gravitational pull acts like a spoon stirring a cup of tea, focusing the outflow of material into two powerful jets shooting out from the star's poles. This creates the characteristic two-lobed structure. The stunning nested lobes of the Southern Crab suggest this process may have happened in distinct episodic bursts, with a second, more recent outflow expanding within the cavity created by the first. But binary interactions are not the only force sculpting these nebulae. Another powerful, invisible hand is thought to be at work: magnetic fields. As the progenitor star spins during its final collapse, its magnetic field lines can be wound up and amplified, becoming incredibly strong. These fields can then channel the outflowing gas, funneling it along the magnetic poles and preventing it from expanding in other directions. It is the cosmic equivalent of squeezing a water balloon in the middle. The pressure escapes forcefully from the two ends. In many cases, it is likely a combination of a binary companion and a strong magnetic field that works in concert to create the most elaborate shapes. The companion star provides the initial asymmetry, while the magnetic fields provide the precise collimation or focusing needed to produce the sharp, jet-like features we observe. Studying these nebulae in the LMC is therefore about more than just appreciating their beauty. It is a crucial investigation into the chemical enrichment of the universe. The gas expelled in a planetary nebula is rich in heavy elements like carbon, nitrogen, and oxygen, the very building blocks of planets and life. By analyzing the light from these nebulae, astronomers can take a census of these elements. Because they all lie at a known distance, the measurements of their brightness and chemical composition are directly comparable, providing a clear picture of how different types of stars contribute to the galactic supply of raw materials. The bizarre shapes of planetary nebulae are not just a curiosity. They are a signature of the complex physical processes that govern the death of stars, processes that ultimately determine how the elements forged in stellar cores are recycled into the cosmos. Each peculiar form, from the delicate butterfly to the mechanical crab, is a fossil record of a gravitational dance or a magnetic struggle, a final message from a star that refused to go quietly into the night. The grand, warped structure of the Large Magellanic Cloud is a testament to the gravitational bullying it endures from our Milky Way. But the evidence of this cosmic interaction is not confined to the galaxy's visible disk. It is written across the entire sky in the form of a faint, ghostly river. Stretching for more than 500,000 light-years, arching over 180 degrees across the celestial sphere, is the Magellanic Stream. This colossal structure is not made of stars but of a tenuous ribbon of hydrogen gas, a cosmic scar left by the slow-motion destruction of the Magellanic Clouds as they orbit our galaxy. Imagine a pair of satellites so thoroughly harassed by their giant host that they are being slowly unraveled, leaving behind a trail of their own essence like breadcrumbs across the void. The Magellanic Stream is precisely that, a tidal tale of epic proportions, and its existence tells a story of a dramatic, ongoing struggle. The process of its formation is a tale of relentless gravitational forces. The Milky Way's immense gravity exerts a powerful tidal pull on both the large and small Magellanic Clouds. The side of each galaxy facing the Milky Way feels a stronger pull than the side facing away, just as the ocean on the side of Earth facing the Moon bulges outward. But because the clouds are also gravitationally bound to each other, orbiting one another as they both orbit the Milky Way, the situation becomes incredibly complex. As they swing around our galaxy, the differential gravitational force, the tidal pull, acts like a cosmic taffy puller, stretching the clouds and literally stripping gas from their outer regions. This stolen material doesn't just fall into the Milky Way immediately. Instead, it gets flung out into a long, trailing arc, a stream of gas that traces the orbital path of the clouds over billions of years. The gravitational interaction between the LMC and the SMC themselves further stirs the pot, with their close encounters helping to pull even more gas loose, contributing to the stream's immense length. For a long time, this seemed like a neat explanation, but when astronomers began to take a detailed inventory of this cosmic river, they encountered a profound and baffling mystery. They carefully measured the total amount of hydrogen gas within the Magellanic Stream and its leading counterpart, a fainter structure known as the leading arm that appears to be rushing ahead of the clouds toward the Milky Way. The combined mass of this gas is staggering. It totals more than 1 billion times the mass of our Sun. The puzzle emerges when you compare this number to the galaxies that supposedly lost it. If you add up all the neutral hydrogen gas currently residing within both the large and small Magellanic Clouds today, the total is significantly less than the mass of gas found in the stream alone. It's as if a crime scene investigator found a pool of blood at a scene that is larger than the total volume of blood inside the suspect. The numbers simply do not add up. The stream contains more gas than the parent galaxies possess now, suggesting that the Magellanic System must have been far more massive and gas-rich in the past than it appears today. This discrepancy has forced scientists to reconsider the entire history of our galactic neighbors. The leading theory to resolve this paradox is that the Magellanic Clouds were not always the relatively small, disrupted satellites we see now. Billions of years ago, they may have been part of a much larger system, perhaps even a substantial group of galaxies that ventured too close to the Milky Way. Within this group, there could have been a third, more massive companion that has since been completely torn apart and assimilated by the Milky Way. The vast reservoir of gas we see in the stream could have been stripped primarily from this now vanished third galaxy, its identity lost to time, with the surviving LMC and SMC contributing a smaller portion. Another compelling idea is that the clouds were once surrounded by an enormous, extended corona of hot gas, a diffuse halo that was easier for the Milky Way's gravity to strip away than the denser gas within the galactic disks themselves. As this hot gas was pulled out, it could have cooled and condensed to form the neutral hydrogen we now detect in the stream, accounting for the missing mass. The implications of this are enormous. It suggests that the Magellanic System is a remnant of a much grander cosmic structure, a ghost of a former grouping that is in its final act of disintegration. The stream is not just a trail of debris, it is a fossil record of a more majestic past. Furthermore, this river of gas is not a permanent feature. It is gradually falling toward the Milky Way, and in the far future, this primordial fuel, largely untainted by the heavy elements forged in multiple generations of stars, will rain down upon our galaxy. This infusion of fresh, pristine hydrogen could trigger new waves of star formation in the Milky Way's outer halo, influencing its chemical evolution for eons to come. The Magellanic Stream, therefore, is far more than a beautiful celestial curiosity. It is a vital clue to understanding the dynamic and often destructive interactions that shape galaxies over cosmic time, a silent witness to the fact that even the grandest cosmic structures are not immune to the relentless pull of gravity. Deep within the chaotic heart of the Tarantula Nebula lies a stellar metropolis so dense and so brilliant that it defies simple comprehension. This is the R136 superstar cluster, a celestial city where stars are packed together with an intensity unmatched in our local universe. If you were to take a volume of space centered on our Sun and extend it just a few light years in every direction, you would find yourself alone with the next star system, Proxima Centauri, a vast emptiness away. Now transport that same volume of space to the core of R136. Instead of one star, you would be surrounded by hundreds of thousands. The night sky from a hypothetical planet within this cluster would be a permanent, blazing daylight, filled with stars separated by distances comparable to those within our own solar system. This is the realm of stellar giants, and the conditions here are so extreme that they force us to rewrite the textbooks on how stars are born and what they can become. R136 is the archetypal superstar cluster, a class of objects that represents the most intense mode of star formation possible. These are not the gently forming open clusters like the Pleiades in our Milky Way. They are cosmic factories operating at maximum capacity, forging stars in a frantic, pressurized burst. The key to their existence is sheer scale. An immense cloud of gas containing the mass of millions of suns undergoes a catastrophic gravitational collapse. Instead of fragmenting into a few dozen stars, it shatters into a vast multitude all at once, creating a densely packed stellar environment that is essentially a snapshot of the early universe when such monstrous clusters were common. R136 is the closest and brightest example we have, a natural laboratory for studying the violent physics that governed the cosmos billions of years ago. The most direct challenge R136 presents is to the theoretical upper limit for star size. For decades, astrophysicists used computer models to predict that stars could not form with masses greater than about 150 times that of our Sun. The reasoning was elegant. The radiation pressure from a newborn star becomes so intense beyond this point that it pushes away the very gas cloud it is feeding from, effectively shutting off its own growth. It's like trying to light a candle in a hurricane. The flame blows itself out. Yet, when astronomers pointed their most powerful telescopes, including the Hubble Space Telescope and now the James Webb Space Telescope at R136, they found stars that scoff at this limit. Several behemoths with names like R136A1 were measured to have initial masses staggering upwards of 250, even 300 solar masses. These are not just large stars, they are stellar monsters that burn with the brightness of millions of suns, living lives of furious intensity that last only a few million years before meeting a spectacular end. The presence of these ultra-massive stars forces a re-evaluation of star formation itself. How did they overcome the radiation pressure barrier? The answer likely lies in the uniquely chaotic environment of a superstar cluster. In R136, star formation is not a clean, isolated event. It is a messy, competitive process where multiple protostars are forming in incredibly close proximity. The intense gravitational interactions and the overwhelming pressure from the surrounding gas may allow these embryonic stars to continue accreting material through complex channels, bypassing the limits that would apply to a star forming in isolation. It's the difference between a single plant growing in a field versus one growing in a dense, competitive rainforest. The rules for survival and growth are fundamentally different. Studying these giants in R136 is therefore crucial, as they are the primary producers of heavy elements and the drivers of the cluster's evolution through their powerful winds and eventual supernova explosions. But the mysteries of R136 extend beyond the lives of individual stars to the dark heart of the cluster itself. In such a crowded environment, stellar close encounters are not rare events. They are a fundamental part of the ecosystem. Stars whip past each other at tremendous velocities, and sometimes their paths cross too closely. When two stars collide, they can merge into a single, more massive object. In a place like R136, this process can become a runaway chain reaction. Sequential collisions could build up an object of hundreds, even thousands of solar masses. Such a stellar Frankenstein's monster would be unstable, burning through its fuel in a geological instant before its core collapses under its own immense gravity. The result, not a typical stellar mass black hole, but something even more intriguing, an intermediate mass black hole. These objects, with masses ranging from a few hundred to a few 100,000 suns, are the universe's missing link. We have solid evidence for small black holes formed from single stars, and we have confirmed the existence of supermassive black holes weighing millions or billions of solar masses at the centers of galaxies. But the intermediate mass black holes, the potential seeds from which the supermassive ones grew, have been elusive. The core of R136 is a prime hunting ground for them. The relentless stellar dynamics there provide a perfect recipe for creating one through repeated mergers. Astronomers search for the telltale signs, the unexplained, rapid orbits of stars near the cluster's center, suggesting they are whirling around a massive, unseen object or a faint glimmer of X-rays from gas being accreted onto a dark central engine. Finding an intermediate mass black hole in R136 would be a monumental discovery. It would validate a key pathway for black hole growth in the universe and provide a direct link between the death of the most massive stars and the birth of the gravitational giants that rule galaxies. It would also transform our understanding of superstar clusters, suggesting they are not just stellar nurseries but also cradles for these intermediate mass black holes, which may themselves be ejected to wander the galaxy during future cluster interactions. R136 is therefore more than a collection of brilliant stars. It is a cosmic crucible where the fundamental laws of physics are tested to their limits, producing outcomes that are both beautiful and terrifying in their scale. Moving from the intense, youthful core of R136, we now turn our attention to a different kind of stellar population, one that speaks of quiet, patient aging rather than violent birth. Scattered across the Large Magellanic Cloud are stars in their final, luminous stages of life known as carbon stars. These are not the brilliant blue giants of the Tarantula Nebula. They are cool, red, and elderly. They have exhausted the hydrogen fuel in their cores and have begun to fuse helium, a process that leads to a remarkable internal transformation. Deep within their bloated atmospheres, nuclear reactions produce an abundance of carbon, which is then dredged up to the surface by powerful convection currents. This infusion of carbon soot fundamentally alters the star's chemistry, allowing carbon molecules to form in its outer layers. These molecules have a unique property. They absorb blue light very efficiently, making the star appear an intense, deep red. A carbon star is essentially a cosmic fireplace, glowing with the ruddy light of its own internal ash. Given that these stars represent a natural, late phase in the life of sun-like stars, you would expect to find them distributed evenly throughout the galaxy, wherever older stars reside. But when astronomers began to map their locations within the Large Magellanic Cloud, they discovered a pattern that was anything but even. Instead of being scattered uniformly, the carbon stars show a pronounced preference for the galaxy's outer fringes, its halo and its distant spiral arm. The central bar region, which contains the majority of the LMC's stellar mass, is curiously deficient in these ruby-red giants. This is the cosmic equivalent of conducting a census of a country's population and discovering that almost all the senior citizens live in the rural countryside, while the city centers are populated almost exclusively by young adults. This anomalous distribution is not a random fluke. It is a profound clue, a fossilized record etched in starlight that reveals the sequence in which the galaxy built itself over billions of years. The explanation for this strange pattern lies in the history of star formation. Stars are not all born at the same time. A galaxy grows and evolves, with different regions igniting their stellar nurseries at different epochs. The concentration of carbon stars in the outer regions of the LMC tells a clear story. Those outskirts are the galaxy's oldest neighborhoods. The stars there formed first, many billions of years ago, from the primordial gas that initially coalesced to create the galaxy. Having had ample time to age, a significant fraction of the intermediate mass stars in these regions have now reached the final chapter of their lives, evolving into the carbon-rich giants we observe today. They are the original inhabitants, the first generation to light up the LMC. In stark contrast, the central bar represents a much more recent chapter in the galactic story. This dense, warped structure is not a primordial feature. It is a dynamic entity that likely formed or was significantly strengthened through interactions and the slow internal evolution of the galaxy over time. The process of forming the bar involved funneling vast amounts of gas inward, which in turn triggered intense and prolonged episodes of star formation. This means that the stars we see in the central bar are, on average, significantly younger than their counterparts in the outer halo. They are still burning hydrogen steadily in their cores, with billions of years of life ahead of them before they will ever enter the carbon star phase. There simply hasn't been enough time for a large population of these younger stars to age into the red giant stage required to become carbon stars. The inner city is still too youthful to have developed a large elderly population. This distribution pattern provides a powerful independent confirmation of the tidal harassment the LMC has endured from the Milky Way. The gravitational pull from our galaxy is thought to have played a key role in driving gas inward, fueling the more recent star formation in the central regions. Furthermore, studying the specific properties of the carbon stars themselves adds another layer of detail to this history. By analyzing their light, astronomers can determine their exact chemical composition. Since carbon stars are factories that produce and distribute carbon into the interstellar medium, the amount of carbon and other elements found in their atmospheres serves as a time capsule. It reveals the chemical conditions of the gas cloud from which the star formed long ago. The carbon stars in the outer halo tend to have lower overall abundances of heavy elements like iron compared to stars in the bar, confirming that they were born from a more pristine, less chemically enriched gas, another hallmark of an older generation. So, the simple act of mapping where these crimson stars live allows us to read the LMC's biography, chapter by chapter, understanding not just where its stars are now, but when they were born and how the entire system has matured over the eons. From the patient chronology written in the distribution of carbon stars, we now turn to a phenomenon of pure, high-energy violence, a signature of power so immense it has left an imprint on the very space surrounding the galaxy. While our view of the Large Magellanic Cloud is often dominated by its brilliant stars and glowing nebulae, some of its most dramatic features are completely invisible to our eyes. They reveal themselves only through the most energetic light in the universe, gamma rays, and recently, astronomers utilizing the Fermi Gamma Ray Space Telescope uncovered one of the most startling structures yet, a pair of colossal, faint bubbles of gamma-ray emission ballooning out from the galactic disk, stretching tens of thousands of light-years into the emptiness above and below. These are the LMC's gamma-ray bubbles, and their discovery immediately brings to mind a similar, though far larger, structure in our own cosmic backyard, the Milky Way's Fermi bubbles. The Fermi bubbles in our galaxy were a major surprise when discovered just over a decade ago. They are vast hourglass-shaped structures emanating from the galactic center, towering 25,000 light-years above and below the plane of the Milky Way. Their existence pointed to a colossal, ancient explosion or a period of intense activity from the region around our supermassive black hole, Sagittarius, a star that occurred millions of years ago. The gamma-ray bubbles in the LMC are a scaled-down version of this phenomenon, but their presence in a smaller, irregular galaxy is in many ways even more puzzling. It suggests that the process which creates these gigantic outflows is not unique to grand spiral galaxies like our own, but may be a fundamental part of galactic evolution, even for galaxies that lack a clearly defined active core. So what could have blown these enormous bubbles in the LMC? The leading theory points to a past period of extreme energy release from the galaxy's center. Imagine a colossal burst of energy, a cosmic eruption that punches outward from the galactic disk, pushing the tenuous gas of the interstellar medium aside and creating a vast, expanding cavity. The gamma-ray emission itself comes from the interaction within the bubble's shell. As this outflowing material plows through space, it creates shock waves that accelerate particles, primarily electrons, to velocities approaching the speed of light. These ultra-relativistic electrons then collide with photons of lower energy light, such as those from the cosmic microwave background, the leftover glow from the Big Bang boosting them up to the incredibly high energies we detect as gamma rays. The bubbles are, in effect, a lingering echo of a past cataclysm, their faint glow a testament to particles that are still ricocheting within a structure created by a short-lived but immensely powerful event. The central mystery, however, lies in identifying the engine that could have produced such a powerful outburst. In the Milky Way, the prime suspect is our centrally located supermassive black hole. The theory is that Sagittarius, a star, had an active phase in the relatively recent past, consuming large amounts of gas and unleashing powerful jets of plasma that inflated the Fermi bubbles. This presents a profound challenge for the LMC because, as we explored earlier, there is no obvious supermassive black hole residing at its center today. The galaxy's heart appears strangely quiet. This forces astronomers to consider several compelling and somewhat dramatic alternatives. One possibility is that the gamma-ray bubbles are the accumulated result of many smaller events rather than one single explosion. The central region of the LMC, particularly its warped bar, has been a site of vigorous star formation for eons. If a large number of massive stars reach the end of their lives in a relatively short period of time, a phenomenon known as a starburst, The combined force of their supernova explosions and powerful stellar winds could have collectively blown a gigantic superbubble that then evolved into the gamma-ray structure we see today. This would be a scaled-up version of the process that creates the superbubbles we see within the galaxy's disk, but operating on a truly galactic scale. The other, more exotic explanation brings us back to the tantalizing theory of a runaway supermassive black hole. If a massive black hole was indeed ejected from the galactic center billions of years ago, the process of its ejection would not have been gentle. The violent merger and recoil that flung it into the darkness would have been an event of unbelievable energy, potentially unleashing a titanic shockwave that could have inflated these very bubbles. Alternatively, perhaps the black hole was active and feeding just before it was ejected, and its final outburst of energy as it was dethroned created the structures. A third scenario involves a past, now dormant, active galactic nucleus, a phase where the galaxy's central black hole, whether it is still there or not, was actively accreting matter and shining brilliantly, powering jets that carved out these cavities. Pinpointing the exact cause is the key challenge. The size and shape of the bubbles hold clues about the duration and intensity of the energy injection. A short, sharp explosion would create a different structure than a sustained, wind-like outflow over millions of years. By carefully mapping the gamma-ray emission and comparing it to observations in other wavelengths, like X-rays and radio, scientists hope to distinguish between these scenarios. The gamma-ray bubbles of the LMC are therefore more than just a fascinating spectacle. They are a frozen moment in the galaxy's energetic history. They force us to look past its current, relatively tranquil state and contemplate a more violent youth, a time when its core may have roared with an intensity that shaped the entire galactic atmosphere. Beyond the vibrant stellar nurseries and the faint echoes of gamma-ray bubbles lies a deeper, more structural puzzle embedded in the galaxy's oldest components. If we compare the galactic family albums of the Large Magellanic Cloud and our own Milky Way, we find a curious discrepancy. Our galaxy is surrounded by a retinue of more than 150 ancient globular clusters, dense, spherical cities of stars that are nearly as old as the universe itself. These clusters are the galactic aristocracy, relics from a time when the cosmos was young. Given that the LMC is a substantial galaxy in its own right, albeit smaller than the Milky Way, we might expect it to possess a similar, if smaller, collection of these ancient stellar fossils. Yet the count is strikingly low. The LMC is home to only a handful of truly ancient globular clusters, a number that seems disproportionately small for a galaxy of its mass and stature. This is the missing globular clusters problem, a quiet anomaly that speaks volumes about the violent history of galactic interactions. The leading theory to explain this absence points directly to the gravitational dominance of our Milky Way. Imagine the LMC not as an independent island, but as a smaller companion that has been orbiting its giant host for billions of years. On each close pass, the Milky Way's immense gravity exerts a powerful tidal force. Just as the Moon's gravity pulls on Earth's oceans, the Milky Way's pull can be strong enough to literally pluck entire globular clusters away from the LMC's outer halo, where they typically reside. These clusters, once bound to the smaller galaxy, are stripped away and captured by the Milky Way, becoming part of our own galactic entourage. Over the eons, this process of galactic theft could have significantly depleted the LMC's original population. In this scenario, some of the ancient globular clusters we see orbiting the Milky Way today might not be native to it at all. They could be stolen property, celestial trophies from a long-term gravitational assault on our neighbor. However, an alternative explanation suggests the difference might be more fundamental, rooted in the very conditions of the LMC's birth. Globular clusters are thought to form during the initial, violent collapse of a giant gas cloud that gives rise to a galaxy. The number and richness of the clusters that form may depend critically on the properties of that primordial cloud, its mass, density, and turbulence. It is possible that the proto-galactic cloud that became the LMC was simply less conducive to spawning a large number of these dense stellar cities. Perhaps it was poorer in the specific pockets of ultra-dense gas required for globular cluster formation, or maybe the early star-forming environment was more hostile, with intense radiation from the first massive stars disrupting the delicate process of cluster formation before they could fully stabilize. In this view, the LMC may have never had a large population to begin with. Its current low count could be a reflection of its inherently different genesis. Resolving this mystery is far more than an exercise in celestial accounting. The population of globular clusters acts as a fossil record of a galaxy's earliest days. Their number, their chemical composition, and their ages provide crucial clues about the hierarchy of structure formation in the universe. Did large galaxies build themselves up primarily by mercilessly cannibalizing smaller ones, stripping them of their stars and clusters, or did they form more monolithically from a single, colossal cloud of gas? The answer likely lies somewhere in between, but the case of the LMC offers a unique test. By studying the chemical signatures of its remaining ancient clusters and comparing them to those in the Milky Way's halo, astronomers can look for a family resemblance. If the clusters in the Milky Way's halo have chemical patterns distinct from those that remained with the LMC, it would be strong evidence that they originated from a variety of now devoured dwarf galaxies, not just from the LMC alone. Conversely, if they share a common lineage, it would bolster the stripping hypothesis. Understanding this helps us piece together the complete life story of our local galactic group. It tells us whether the LMC is a relatively pristine survivor that has managed to hold onto its identity despite the Milky Way's influence, or a ghost of a formerly more massive system that has been systematically dismantled over cosmic time. The missing clusters are not just an absence, they are a silent testimony to the forces that have shaped the galaxies we see today. A reminder that the peaceful appearance of the night sky belies a history of gravitational struggle and cosmic evolution on the grandest scales. But the gravitational pull of the Milky Way is not the only force acting upon its satellite. There is also the subtle, continuous friction of moving through an invisible ocean. As the Large Magellanic Cloud speeds along its billion-year orbit, it isn't traveling through a perfect vacuum. It is plowing through the extremely thin but pervasive gas that fills the vast halo of our galaxy. This interaction creates a phenomenon known as ram pressure, and it acts upon the LMC like a cosmic headwind, relentlessly scouring its surface and reshaping its very structure in a process we can observe in real time. To grasp the concept of ram pressure, imagine sticking your hand out of the window of a moving car. Even on a calm day, you feel a strong force pushing against your palm. That force isn't from the wind itself, but from the pressure of the stationary air molecules piling up against your moving hand. Now, scale that idea up to a galactic level. The LMC is the moving hand, and the diffuse million-degree gas of the Milky Way's halo is the stationary air. Although this intergalactic medium is incredibly sparse, often just a few atoms per cubic meter, the sheer speed and size of the LMC make the cumulative effect tremendous. This ram pressure acts as a stripping force, pushing against the LMC's own reservoir of gas and dust, the raw material for future stars. The most direct and observable signature of this ongoing assault is a distinct warping of the LMC's gaseous disk. When astronomers map the distribution of neutral hydrogen gas, which traces the galaxy's primary fuel supply, they don't see a perfectly flat, symmetrical plane. Instead, the disk appears bent and distorted, much like a flag flapping in a strong breeze. The side of the LMC that is leading its orbital motion forward bears the brunt of the ram pressure. The gas on that leading edge gets compressed and heated, while on the trailing side the pressure is lower, allowing the gas to flow outwards in a subtle wake. This asymmetry is a clear fingerprint of the galaxy's motion through the halo, a dynamic deformation that would not exist if the LMC were floating in isolated space. This relentless pressure has a more profound consequence than just bending the disk. It is actively stealing the LMC's future. Ram pressure can overcome the LMC's relatively weak gravity, particularly in its outer regions where the gravitational hold on gas clouds is most tenuous. As the galaxy moves forward, the pressure effectively blows these tenuous clouds away, like dust being swept from a table. This stripped gas is then lost to the intergalactic void or captured by the Milky Way, adding to the complex stream of material we see trailing the galaxy. This process directly limits the galaxy's ability to form new stars, as it is being systematically drained of its stellar fuel. We are witnessing a form of galactic starvation, where the LMC is being prevented from replenishing the gas it consumes through each generation of star birth and death. What makes this phenomenon so valuable to astronomers is that it provides a live action demonstration of a key process that shapes galaxies throughout the universe. In dense galaxy clusters like the famous Coma cluster, this same ram pressure stripping is observed on a far more violent scale. Galaxies moving through the dense intracluster medium can have their gas completely ripped away in a single pass, transforming them from gas-rich spirals into red and dead ellipticals, devoid of the material needed to make new stars. The LMC offers us a closer, slower motion view of this same fundamental physics. By studying how the ram pressure affects our neighbor, we can calibrate our models and better understand how environment dictates a galaxy's evolution, ultimately determining its lifespan and appearance. The subtle bending of the LMC's gas disk is therefore more than a curiosity. It is a textbook illustration of cosmic forces at work, a lesson in galactic interaction written across the sky. But beyond the dynamics of entire clusters and galaxies, some of the most profound mysteries are hidden within the peculiar light of a single, unassuming star. Tucked away in the Large Magellanic Cloud is a variable star known as HV 2112, and for a brief, exciting period, it was at the center of one of the most tantalizing theoretical predictions in all of astrophysics. This star appeared to be a living, breathing candidate for something that had never been conclusively observed, a Thorne-Zitkow object. The very concept sounds like science fiction. Imagine a star within a star, a dense, city-sized neutron star, the collapsed core of a once massive sun, orbiting not around but deep inside the vast, bloated atmosphere of a red supergiant. This isn't a binary system where two stars dance at a distance. It is a cosmic Matryoshka doll, a bizarre hybrid where one stellar corpse serves as the engine for a still living giant host. The theory, proposed by physicists Kip Thorne and Anna Zitkow in the 1970s, describes how such an object could form. In a dense stellar environment, a neutron star could be captured by a red supergiant, spiraling inward through its tenuous outer layers until it comes to rest at the giant's core. Alternatively, it could be the result of a rare, non-supernova collapse where the outer layers of a massive star fall back onto the newborn neutron star, enveloping it without destroying it. Once embedded, the neutron star's immense gravity and heat would fundamentally alter the nuclear fusion processes happening within the red supergiant. It would no longer be a normal star. It would become a unique factory for producing exotic elements, its interior operating under a set of physical rules unlike any other star in the universe. The excitement around HV 2112 began when astronomers analyzed its light and found a chemical fingerprint that was bizarrely out of place. The star's atmosphere showed unusually high abundances of heavy elements like rubidium, lithium, and molybdenum. In a typical red supergiant, these elements are not produced in significant quantities. Lithium, in particular, is a fragile element that is normally destroyed by the high temperatures in stellar interiors. Its presence in such large amounts was a major red flag, a signal that something unusual was happening deep within the star. These peculiar abundances matched precisely what theoretical models predicted for a Thorne-Zitkow object. The intense temperatures and unique density gradients around the neutron star core were thought to trigger a specialized nuclear chain reaction known as the slow neutron capture process, or S process, which would efficiently produce exactly the suite of exotic elements observed. It seemed for a moment that a 40-year-old prediction had been spectacularly confirmed. However, in science, extraordinary claims demand extraordinary evidence, and the initial discovery sparked a vigorous and necessary debate. Other research teams reanalyzed the data, applying different models and corrections. Some argued that the chemical signature, while unusual, could potentially be explained by a more conventional, though still rare, type of highly evolved star. An asymptotic giant branch star, or a GB star, in a very specific and brief phase of its life, can also experience bursts of neutron capture that produce heavy elements. The debate hinged on subtle details in the spectral lines and the precise temperature and luminosity of HV 2112. Was it a true supergiant, as required for the Thorne-Zitkow object hypothesis, or was it a lower luminosity, a GB star that merely mimicked the chemical signature? The astronomical community found itself divided, with the star's true nature hanging in the balance. The case of HV 2112 is a perfect example of the scientific process at work on the frontier of knowledge. It highlights the challenge of interpreting subtle signals from across a vast interstellar distance. A single measurement, a particular spectral line, can support a revolutionary idea or a more mundane one. The follow-up observations have not yet provided a definitive answer, and the star remains a fascinating enigma. Whether it is ultimately confirmed as the first Thorne-Zitkow object or reclassified as an unusual variant of a known star type, its study has pushed our understanding of stellar evolution and nucleosynthesis. It reminds us that the universe is capable of producing configurations far stranger than our standard textbooks allow, and that the hunt for these theoretical curiosities is a driving force behind some of the most cutting-edge observations in modern astronomy. But the forces that shape the Large Magellanic Cloud are not only written in the motions of its gas or the warping of its bar. They are also painted in bright, sharp detail across the canvas of its newest stars. When astronomers map the locations of the galaxy's youngest star clusters, those brilliant blue groupings of stars less than 100 million years old, they uncover a striking and immediate asymmetry. These clusters are not scattered evenly throughout the galactic disk. Instead, they are overwhelmingly concentrated on the western side of the galaxy, creating a lopsided distribution that is impossible to ignore. It's as if a cosmic artist, when decorating the LMC, dipped their brush most heavily on one specific quadrant, leaving the eastern regions comparatively bare of these youthful stellar congregations. This is not a random pattern. It is a direct and dynamic consequence of the galaxy's gravitational relationships, a real-time snapshot of how interactions sculpt star birth. The primary force behind this lopsided starburst is the relentless tidal pull from our own Milky Way. As the LMC travels along its orbit, it experiences a gravitational gradient. The side of the galaxy closer to the Milky Way feels a stronger pull than the side farther away. This difference in force stretches the entire galaxy, but it does more than just warp its shape. This tidal influence has a profound effect on the galaxy's internal gas, the raw material for making stars. Imagine the LMC's vast reservoirs of hydrogen gas as an immense placid lake. The Milky Way's gravity acts like a giant hand pressing into one side of that lake. The pressure compresses the gas, increasing its density and making it more prone to gravitational collapse. On the western side of the LMC, the side currently leading its orbital motion and feeling the strongest compressing force, this tidal pressure is at its peak. Here, giant molecular clouds are squeezed just enough to cross the critical threshold, triggering a chain reaction of collapse that ignites new star clusters. The western side becomes a preferred construction zone for stellar nurseries, while the eastern side, experiencing a weaker tidal force, remains relatively quiescent. Adding another layer of complexity to this gravitational dance is the influence of the Small Magellanic Cloud. The LMC and SMC are a bound pair, locked in a mutual orbit that takes about 900 million years to complete. Their close passages are not gentle flybys. They are significant gravitational events that send strong ripples through both galaxies. During these encounters, the gravitational pull from the SMC can torque and compress the gas within the LMC, further enhancing the star-forming activity on specific regions. The combined gravitational effects of both the Milky Way and the SMC create a complex, shifting landscape of pressure across the LMC's disk. Currently, the alignment of these forces favors the western side, creating the observed hotspot of recent cluster formation. This makes the LMC a living laboratory for studying what astronomers call tidal triggering, where the gravitational influence of a neighbor directly dictates where and when a galaxy gives birth to new stars. This asymmetric distribution provides a powerful key to understanding the recent history of the Magellanic System. The pattern of young clusters acts like a footprint, preserving a record of the gravitational forces that have been acting on the galaxy over the past several hundred million years. By studying the exact ages of these clusters, astronomers can perform a form of cosmic forensics. If the clusters on the western side all have similar, very young ages, it suggests a single, recent burst of activity, perhaps triggered by the LMC's last closest approach to the Milky Way. If, however, the ages show a gradient with slightly older clusters found further from the current epicenter of activity, it would indicate a more sustained, wave-like progression of star formation driven by the galaxy's ongoing orbital motion. Each cluster's age is a timestamp, allowing scientists to reconstruct the timeline of this galactic interaction. The implications extend far beyond our local group. Similar asymmetries are observed in other satellite galaxies and in galaxies within dense clusters. The phenomenon seen so clearly in the LMC demonstrates that a galaxy's star-forming activity is not always an internal affair. It can be powerfully governed by its external environment, by the gravitational pushes and pulls of its neighbors. For a smaller galaxy like the LMC, this external forcing can dominate its evolution, effectively determining its destiny by regulating its ability to form new stars. The lopsided splash of young clusters is therefore more than just a curious imbalance. It is a vivid, ongoing demonstration of a fundamental process that shapes galaxies across the universe, a process where solitude is a luxury and interaction is the rule. Yet another layer of the galaxy's hidden energy reveals itself not in the brilliant light of its stars, but in a pervasive, ghostly glow that bathes the entire system. When astronomers point telescopes sensitive to far ultraviolet light toward the Large Magellanic Cloud, they detect a diffuse, widespread emission that is far too extensive to be coming solely from the surfaces of the known hot young stars. These massive blue stars do blaze fiercely in the ultraviolet, but their light is concentrated in specific, localized regions like the Tarantula Nebula. The mystery is the background hum, a faint, uniform luminescence that spreads across the vast stretches of seemingly empty space between the stellar hotspots. It's as if the entire galaxy is immersed in an invisible energy field, a soft ultraviolet fog whose source remains unidentified, forcing scientists to consider explanations that range from the exotic to the truly revolutionary. The first and most conservative theory points to a vast, unseen population of stellar corpses. White dwarfs are the Earth-sized embers left behind when sun-like stars die. They are incredibly dense and initially extremely hot, cooling down over billions of years. While a single white dwarf is faint, the combined light from millions of them spread throughout the galaxy could, in theory, add up to a significant diffuse glow. The challenge is that our current surveys might miss the faintest and most numerous of these objects, especially if they are old and have cooled considerably. If the LMC holds a larger than expected population of these faint, hot white dwarfs, their collective ultraviolet light could be the missing piece of the puzzle. This would imply that our census of stellar remnants is incomplete, and that the galaxy's history of star formation produced far more of these long-lived cinders than previously estimated. However, an alternative and far more speculative explanation ventures into the realm of particle physics. This theory suggests that the diffuse ultraviolet light might not be starlight at all, but rather a signature of dark matter itself. One of the leading candidates for dark matter is a hypothetical particle called the action. If actions exist, they could theoretically decay or convert into photons, particles of light, when they pass through intense magnetic fields, such as those found permeating the galaxy. The energy of these photons would fall precisely within the far ultraviolet range. According to this idea, the pervasive glow we see is not a product of stars, but the faint, steady radiance of dark matter particles decaying throughout the entire volume of the LMC. The glow would be diffuse because the dark matter halo is diffuse, perfectly matching the observed widespread emission. This creates a fascinating dilemma for astronomers. Is the ultraviolet glow a testament to a vast population of ordinary, if unseen, stellar remnants, or is it the first indirect glimpse of a fundamental particle that makes up most of the matter in the universe? Distinguishing between these possibilities requires meticulous observation. Researchers are carefully mapping the precise distribution and intensity of the ultraviolet light, looking for subtle clues. If the glow is from white dwarfs, its pattern should correlate with the distribution of the galaxy's older stellar population, tracing the places where stars have lived and died over billions of years. If, however, the glow is from actions, its distribution should instead follow the much larger spherical halo of dark matter that envelops the entire visible galaxy, potentially showing a different and smoother pattern. Resolving this mystery is critical for completing the galaxy's energy budget and accounting of all the energy being produced and absorbed. Just as an accountant must balance a company's books, astronomers must account for all the light emitted by a galaxy. An unexplained source of energy like this far ultraviolet glow represents a significant deficit in our understanding. It means we are missing a major contributor to the galaxy's life cycle, whether it is a population of faint stars or a completely new physical process. The Large Magellanic Cloud, with its well-defined distance and relatively face-on orientation, provides the perfect laboratory to conduct this cosmic audit. By solving the mystery of its ultraviolet fog, we don't just learn about one galaxy, we advance our fundamental understanding of what galaxies are made of and how they shine. While we have witnessed the power of gravity to shape galaxies and trigger bursts of star formation, its most extreme application can be seen not in the collective motion of billions of stars, but in the solitary journey of a single runaway sun. Imagine a star not merely orbiting its galactic home, but fleeing from it at a velocity so tremendous that it has achieved escape velocity, destined to travel the intergalactic void forever. This is not a theoretical concept, it is the reality for a class of objects known as hypervelocity stars, and one of the most famous, a brilliant blue star designated He 0437-5439, holds a secret that directly implicates the Large Magellanic Cloud in a dramatic act of cosmic expulsion. The story of He 0437-5439 begins with its discovery as it raced through the halo of our own Milky Way. Measurements of its speed revealed an astonishing figure. It was moving at approximately 2.6 million kilometers per hour. At that velocity, it is not bound by the Milky Way's gravity. It is a fugitive on a one-way trip out of our galaxy. The immediate question for astronomers was a simple one. Where did it come from? By tracing its trajectory backwards across the sky, accounting for the gravitational pull it experienced along the way, the path did not lead to a dramatic event within the Milky Way, like the supermassive black hole at our own galactic center. Instead, the star's origin pointed squarely back toward our neighboring galaxy, the Large Magellanic Cloud. This was a stunning revelation. It suggested that the LMC possessed, or once possessed, the kind of gravitational powerhouse capable of launching a star on such an incredible journey. The most plausible mechanism for this stellar catapult is known as the Hill's mechanism, a process involving a devastating gravitational dance. The scenario begins with a binary star system, two stars orbiting a common center of mass. If this binary pair ventures too close to a very massive object like a black hole, the intricate gravitational fields can tear the partnership apart. In a precise and violent interaction, one of the stars can be captured by the black hole, swinging into a tight orbit around it. To conserve energy and momentum, the other star is flung away at an enormous speed, ejected from the system like a stone from a sling. For a star to reach the hypervelocity we observe with He 0437-5439, the slingshot must be incredibly powerful, requiring a black hole with substantial mass. This is where the mystery deepens, circling back to a recurring theme in the LMC's story, the missing central black hole. To produce a star with this velocity, the black hole involved would likely need to be an intermediate mass black hole weighing several thousand solar masses. The confirmed presence of such an object in the LMC has been elusive. The star's very existence, therefore, becomes indirect but compelling evidence that a black hole of significant mass does or did reside in the heart of our neighbor. It acts as a gravitational smoking gun, a piece of evidence left behind by the perpetrator. The ejection event itself must have occurred millions of years ago, and the star has been traveling through the void between our galaxies ever since, a solitary testament to a past cataclysm. However, a fascinating complication arose when astronomers estimated the star's age. He 0437-5439 is a hot blue main sequence star, and its lifetime is estimated to be around 100 million years. The problem is that at its measured speed, the travel time from the LMC to its current position in the Milky Way's halo is calculated to be around 120 million years. How can a star be younger than its journey? This paradox led to an alternative, equally thrilling hypothesis. Perhaps He 0437-5439 is not a single star but a merged entity. The original object ejected from the LMC could have been a tight binary system itself. During its long voyage, the two stars may have spiraled together and merged, creating a single, more massive and hotter star whose age appears younger because the merger event effectively reset its clock. This elegant solution resolves the timeline discrepancy and adds another layer of dynamism to the story, showcasing how stellar interactions can continue to reshape objects even after they have been flung into the loneliness of intergalactic space. The journey of this hypervelocity star is more than just a thrilling celestial anecdote. It provides a unique probe of the gravitational landscape between galaxies. As it travels, its path is subtly bent by the combined gravitational fields of the Milky Way and the LMC, as well as the extended dark matter halos of both galaxies. By precisely tracking its motion, astronomers can gain insights into the distribution of this invisible mass. Furthermore, the star's composition, revealed by its spectrum, serves as a sample of the chemical environment of the LMC from which it originated. He 0437-5439 is a messenger carrying forensic information about its birthplace across a vast cosmic distance. Its solitary flight underscores the incredible forces that can be unleashed in the hearts of galaxies, proving that even a single point of light streaking through the darkness can tell a story of gravitational violence on an epic scale. As we've seen, the Large Magellanic Cloud possesses a distinct and lopsided personality, but one of its most fundamental anatomical features is a subtle distortion that reveals just how turbulent its life has been. When we picture a galaxy like our own Milky Way, we often imagine a relatively flat, thin disk, a cosmic frisbee of stars and gas spinning smoothly through the void. The LMC, however, defies this simple geometry. Detailed observations confirm that its disk is not flat at all. It is distinctly warped, bending away from a single plane like a vinyl record left too long in the sun. Furthermore, this disk is not razor-thin. It has a significant and measurable thickness, more like a puffy cushion than a sharp blade. This warped and puffy structure is not a random flaw but a direct signature, a fossilized imprint of the galaxy's dynamic and often violent history of gravitational interactions. The primary sculptor of this distortion is the relentless gravitational influence of our Milky Way. The LMC is not moving through a frictionless void. It is orbiting within the immense and diffuse halo of hot gas that surrounds our galaxy. As it travels, it experiences a continuous force known as ram pressure, which we discussed earlier, but it also feels a powerful tidal force. This tidal pull is the same type of force that the Moon exerts on Earth's oceans, but scaled up to a galactic level. The side of the LMC closer to the Milky Way feels a stronger gravitational tug than the side farther away. This difference in force stretches the entire galaxy, pulling it out of its natural flat shape. Over millions of years, this persistent tug-of-war has systematically twisted the disk, creating the observed warp. It's a slow-motion deformation, a cosmic battle where the Milky Way's gravity is constantly trying to pull our neighbor apart, leaving its disk permanently bent. But the plot thickens when we consider the role of the small Magellanic Cloud. The gravitational dance between these two satellite galaxies is far more intimate and chaotic than their individual orbits around the Milky Way. They have had multiple close encounters over billions of years, each passage sending powerful gravitational shockwaves through their structures. During these flybys, the pull of the SMC can torque the LMC's disk, adding another layer of twisting and thickening. Imagine holding two wet sponges and slamming them together. The resulting shape is messy, distorted, and thickens as material is pushed outward. The gravitational interactions between the LMC and SMC have a similar effect on their stellar and gaseous components. Stars and gas clouds are gravitationally stirred up, their orbits perturbed so that they oscillate above and below the galactic plane, contributing to the overall puffy thickness of the disk. This dynamic past has essentially given the LMC a case of galactic osteoporosis, weakening its structural integrity and making it more susceptible to deformation. Studying the precise nature of this warp is far more than an academic exercise in galactic anatomy. It is a powerful tool for cosmic detective work. The specific shape and amplitude of the warp act as a detailed recorder of the gravitational forces that have acted upon the LMC. By creating sophisticated computer models, astronomers can essentially run the movie of the Magellanic System's history backwards. They input different possible scenarios for the past orbits of the LMC and SMC around the Milky Way, along with estimates of their masses, and let the simulation run. The model that produces a warp matching the one we observe today is considered the most accurate reconstruction of their true history. This process allows scientists to constrain critical unknown factors, such as the total mass of the LMC's dark matter halo. A more massive halo would provide a stronger gravitational anchor, resisting the warping forces more effectively than a lighter one. The observed degree of warp, therefore, helps pin down that elusive mass value. This galactic forensics has led to a significant revision of our understanding of the Magellanic Cloud's journey. For a long time, it was thought they might be on their first infall toward the Milky Way. However, the pronounced and complex nature of the LMC's warp strongly suggests a much longer and more dynamic relationship. The distortions we see are likely the accumulated result of multiple pericenter passages, the closest points of approach to the Milky Way over many billions of years. Each close pass would have added another twist to the disk, Furthermore, the models that best reproduce the warp often require a recent, close encounter between the LMC and SMC, perhaps as recent as 200 to 300 million years ago. This event would have been a major galactic trauma, violently stirring both galaxies and leaving an unmistakable signature in their shapes. The warped disk of the LMC is therefore a living historical document, its curves and thickness preserving a billion-year chronicle of gravitational encounters, a story of cosmic companionship and conflict written in the very positions of its stars. But beyond the grand architecture of warped disks and the brilliant glow of young stars, some of the galaxy's most intriguing messages are written in a subtler language, the language of heat. When astronomers point infrared telescopes toward the Large Magellanic Cloud, they see more than just the warm glow of interstellar dust. They detect a series of distinct, bright emission bands at specific infrared wavelengths, a pattern of spectral lines that acts like a cosmic fingerprint. The mystery is that this fingerprint does not belong to any known atom or simple molecule. These are the unidentified infrared emission bands, a ubiquitous but enigmatic signature that has been observed not just in the LMC, but throughout our own Milky Way and other galaxies. Their presence indicates that a widespread and peculiar substance is being illuminated, a substance that absorbs ultraviolet light from young stars and re-radiates it as this characteristic infrared glow. For decades, the source of these bands was one of the great puzzles of astrochemistry. The prime suspect in this cosmic mystery is a class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. If that name sounds intimidating, the concept is surprisingly familiar. Imagine the sooty residue from a candle flame or the char on a piece of grilled food. At a microscopic level, that soot is made of PAH's sturdy, carbon-based molecules shaped like tiny hexagons linked together in flat sheets, similar to miniature fragments of graphite or graphene. These molecules are incredibly robust. When a PAH molecule is struck by a single photon of ultraviolet light from a hot star, it doesn't shatter. Instead, it vibrates intensely and re-emits that energy at several specific infrared wavelengths, producing the exact pattern of bands we observe. It's a compelling explanation that ties the cosmic mystery to a common earthly substance, suggesting that the basic building blocks of soot are scattered across the galaxy. However, the story in the Large Magellanic Cloud adds a fascinating and complicating twist. When astronomers map the distribution of these infrared bands across the galaxy, they find that it is curiously patchy. The emission is strong in some regions, like the Tarantula Nebula, where massive stars are pumping out immense amounts of ultraviolet light. This makes perfect sense, as that UV energy is what makes the PAHs glow. But in other areas that also have plenty of ultraviolet light, the characteristic bands are surprisingly weak or even absent. It's as if someone has turned down the volume on this particular infrared signal in specific parts of the galaxy. This uneven distribution is the core of the puzzle, and it forces scientists to look beyond the simple presence of starlight to understand the life cycle of these complex molecules. The leading theory to explain this patchiness focuses on the violent environment of the LMC. PAH, while tough, are not indestructible. The intense ultraviolet radiation that makes them glow can, if it is too harsh, also tear them apart. In a region dominated by the most massive and hottest stars, the UV light can be so energetic that it photodissociates the PAH molecules, breaking their carbon bonds and reducing them to simpler atoms and molecules. Furthermore, the shock waves from supernova explosions that ripple through the interstellar medium can be equally destructive, shattering the delicate molecular structures through sheer force. The LMC, with its high rate of massive star formation and supernova, is a particularly hostile environment for complex molecules. The pattern we see, strong PAH emission in some areas and weak emission in others, may be a real-time map of this cosmic balancing act. It shows us where conditions are just right for PAHs to survive and flourish, and where the stellar radiation is simply too fierce, creating zones of molecular destruction. This leads to a deeper implication about the galactic ecosystem. The creation of PAHs is thought to occur in the outflows from aging carbon-rich stars. As these stars die, they expel carbon atoms into space, which can then link up to form these complex chains in the cool, expanding shells of gas. The presence or absence of PAHs in a region therefore tells a story about the journey of cosmic material. It takes time for the products of stellar death to spread and mix with the interstellar medium. If a region has recently been scoured by a supernova blast wave, it may have been cleared of its PAHs, and there hasn't been sufficient time for new ones to form or drift in from quieter neighborhoods. The patchy infrared map of the LMC could be illustrating the turbulent and inefficient process of recycling complex materials throughout a galaxy. We are essentially seeing which parts of the galaxy have a healthy population of these organic molecules and which are still recovering from a recent cosmic catastrophe. Studying this phenomenon in the LMC is particularly valuable because of its lower metallicity. That is, it contains a smaller proportion of heavy elements like carbon compared to the Milky Way. Since carbon is the fundamental ingredient of PAHs, astronomers can investigate how the abundance of these molecules depends on the overall chemical richness of a galaxy. The findings could have profound implications for the potential for life elsewhere. PAHs are considered prebiotic molecules, potential stepping stones toward the even more complex chemistry required for biology. Understanding where they can form, survive, and spread throughout a galaxy informs our ideas about which galactic environments might be most favorable for the emergence of life. The faint, unidentified infrared bands are therefore more than just a spectral curiosity. They are a tracer for the distribution of complex organic matter, and their puzzling patchiness in the Large Magellanic Cloud reveals a dynamic and often destructive cosmic environment where the building blocks of complexity are in a constant struggle between creation and annihilation. This division in the stellar population is not just a statistical oddity, it is a direct reflection of the galaxy's turbulent history. The two distinct branches correspond to two major, separate epochs of star formation, separated by a long period of relative quiet. The stars on the brighter, more metal-rich branch are the younger generation. They formed more recently, perhaps within the last 1 to 3 billion years, from gas that had already been enriched with heavy elements from countless previous stellar generations. Their formation was likely triggered by the very gravitational interactions that have shaped the LMC's lopsided appearance. The close encounters with the small Magellanic Cloud and the growing tidal pull from the Milky Way would have compressed vast reservoirs of this enriched gas, igniting a powerful wave of new star birth that created this populous, younger family of red giants. In contrast, the fainter, more metal-poor branch represents the galaxy's ancient pioneers. These stars are significantly older, with ages stretching back 8, 10, or even 12 billion years. They were born from the primordial gas that first coalesced to form the LMC, a gas that had been scarcely touched by the nuclear furnaces of earlier stars. Their chemical simplicity is a time capsule, preserving the conditions of the early universe within their atmospheres. The long gap between the formation of these two populations suggests a dramatic lull in the LMC's star-forming activity. After its initial burst of creation, the galaxy may have entered a quiescent phase. Its gas reserves too diffuse or too unsettled to collapse into new stars for billions of years. It was only when the galaxy's dynamic environment was violently stirred by its neighbors that the second, more recent epoch of star formation was jump-started. The clarity of this split in the LMC is a gift to astronomers that is unavailable in our own Milky Way. Within our galaxy, red giants are spread across a vast range of distances, making it incredibly difficult to separate true luminosity differences from the effects of sheer distance. But in the Large Magellanic Cloud, because all its stars are essentially the same distance from us, the split appears with stunning precision. This allows scientists to study the properties of each population in isolation, measuring not just their ages and metallicities, but also their distribution across the galaxy. The older, metal-poor stars are found predominantly in the outer halo, the galaxy's original footprint, while the younger, metal-rich stars are concentrated in the central bar and disk, regions revitalized by more recent activity. This spatial mapping confirms the historical narrative written in the color magnitude diagram. Understanding this bifurcated evolutionary path does more than just recount the LMC's past. It provides a crucial benchmark for stellar physics itself. The models that predict how a star of a given mass and composition will evolve and brighten as a red giant can be rigorously tested against these two clear, distinct sequences. The excellent agreement between theory and observation for the LMC's red giant branch gives astronomers great confidence in using these models to determine distances and ages for stars in even more remote galaxies. The split red giant branch is therefore more than a historical record. It is a fundamental calibration tool, a cosmic ruler that helps us measure the scale and timeline of the entire universe. This seemingly technical detail, a split on a graph, ultimately reveals the episodic nature of galactic life, showing that a galaxy's history is written in the very DNA of its stars. When the light from supernova 1987 first reached Earth, it was a brilliant, singular flash, a beacon of stellar death that captivated the world. But the story of that light was far from over. In the months and years that followed, as the initial glare faded, astronomers witnessed something almost magical. The supernova appeared to flare up again, not once but multiple times. These were not new explosions, they were celestial mirages, a phenomenon known as a light echo. Imagine shouting into a vast, complex canyon. You hear your initial shout, but then, a moment later, you hear it again as the sound bounces off a distant cliff face and again from a different wall. A light echo works on the same principle, but with light traveling across unimaginable distances. The initial flash from the supernova raced outwards in all directions. While the light that came straight to Earth arrived in February 1987, other photons from that same flash traveled on slightly longer paths. They journeyed until they struck vast, faint clouds of interstellar dust located in front of and behind the supernova itself. These dust clouds acted like cosmic mirrors, reflecting a small fraction of that light back toward us. Because the reflected light had to travel an extra distance first to the dust cloud and then to Earth, it arrived months or even years later, creating the illusion of a rekindled supernova. These echoes were not merely a beautiful curiosity, they transformed the supernova into a gift that kept on giving, providing a unique form of cosmic time travel. The initial light curve of a supernova, the precise record of how its brightness intensifies and then fades over days and weeks, is incredibly difficult to capture in full detail. Telescopes have limited viewing time, and bad weather or technical issues can cause gaps in the data. But with a light echo, nature itself provides a perfect replay. As the echo unfolded, astronomers were able to re-observe the supernova's entire light curve with exquisite precision, long after the original event had vanished from direct view. It was as if the universe had pressed record on the explosion, allowing scientists to study the playback at their leisure. This remeasurement confirmed details about the explosion's mechanics and the nature of the progenitor star with a level of accuracy that would have otherwise been impossible. Perhaps even more remarkably, the light echoes acted as a powerful probe, illuminating the hidden architecture of space itself. The dust clouds responsible for the echoes are normally completely invisible, too faint and diffused to be seen directly. But when the flash of the supernova lit them up, it revealed their precise shapes and locations in three-dimensional space. Because light travels at a fixed, known speed, The time delay between the initial flash and the appearance of each echo allowed astronomers to calculate the exact distance from the supernova to the dust cloud that created it. By mapping multiple echoes, they could construct a detailed three-dimensional chart of the interstellar medium surrounding the supernova. This was like using a sonar pulse in a dark ocean, with the light echoes revealing the unseen topography of vast, cold dust structures that had lurked undetected in the darkness for millennia. The echoes showed that space is not empty. It is filled with a complex and intricate landscape of these faint, wispy clouds, and supernova 1987 provided the perfect flashbulb to capture a portrait of this hidden world. Moving from the gentle echoes of reflected starlight, we confront a far more energetic and invisible phenomenon, the storm of high-energy particles perpetually raining down on the galaxy. This is the domain of cosmic rays, atomic nuclei accelerated to nearly the speed of light. And when we compare the population saturating the Large Magellanic Cloud to the one we experience in the Milky Way, we find a significant and telling difference. It's as if our two neighboring galaxies are experiencing two distinct types of weather, one a steady downpour and the other a more erratic, yet sometimes more intense squall. This anomaly isn't just a statistical curiosity. It's a direct probe into the fundamental forces that govern a galaxy's most violent processes and its ability to contain the energy they unleash. The primary factories for these cosmic rays are thought to be the same engines that light up the galaxy, supernova remnants. When a massive star explodes, the expanding shockwave acts as a natural particle accelerator of almost unimaginable power. As the blast wave plows through the interstellar medium, it can trap charged particles like protons and atomic nuclei within its magnetic fields, forcing them to bounce back and forth across the shock front. With each crossing, the particles gain energy, much like a tennis ball being volleyed faster and faster between two rackets, until they are eventually flung out into the galaxy, traveling at relativistic speeds. Given that the LMC is home to spectacular supernova remnants and vibrant stellar nurseries like the Tarantula Nebula, we would expect it to be a prolific producer of cosmic rays. Yet, the overall intensity and the energy distribution of these particles within the LMC are not a simple mirror image of what we see at home. One compelling explanation for this discrepancy lies in the galaxy's weaker magnetic field. Magnetic fields play a crucial dual role in the life of a cosmic ray. They are essential for their acceleration within supernova shocks, but they are also the very mechanism that confines them to a galaxy afterward. Without a strong magnetic field to trap them, cosmic rays would simply escape into intergalactic space almost as quickly as they are produced. The Large Magellanic Cloud, being a smaller and less massive galaxy than the Milky Way, is believed to have a significantly weaker overall magnetic field. This means that while supernova in the LMC might accelerate particles just as efficiently as those in our galaxy, a larger fraction of those particles are likely able to leak out, diffusing into the vast void before they can build up to the densities we observe in the Milky Way. The galaxy's magnetic cage is simply less secure, allowing its most energetic particles to slip away. However, the story is complicated by the fact that the LMC is not uniformly deficient in cosmic rays. Observations from gamma-ray telescopes, which detect the light produced when cosmic rays collide with interstellar gas, reveal that specific regions, particularly areas of intense recent star formation, can be brilliantly luminous. This suggests that in these localized hotspots, the cosmic ray density is exceptionally high. This creates a picture of a galaxy with a more patchy and extreme cosmic ray environment compared to the relatively well-mixed and homogeneous population found throughout the Milky Way's disk. The LMC's cosmic ray weather is stormier, with concentrated tempests raging above its stellar nurseries, while the broader galactic environment experiences a weaker, more diffuse drizzle. This patchiness leads to another fascinating possibility. the existence of unique cosmic ray sources within the LMC that have no parallel in our own galaxy. While supernova are the standard engines, theorists have proposed that other, more exotic objects could be contributing. The dense core of the R136 superstar cluster, for instance, is a potential candidate. The frequent stellar collisions and the powerful winds from its hundreds of massive stars could create a continuous and potent acceleration site, a cosmic ray generator that operates differently from a single, isolated supernova blast. Furthermore, if the LMC does host an intermediate mass black hole or even a rogue supermassive black hole, the accretion processes around such an object could launch jets of plasma that are also efficient cosmic ray accelerators. The unique dynamical history of the LMC, including past mergers, may have created a population of such unusual sources that inject a different flavor of particles into the galactic mix. Ultimately, the anomalous cosmic ray population serves as a critical diagnostic tool. By studying how these high-energy particles are distributed and how their energies vary across the LMC, astronomers can indirectly map the strength and structure of the galaxy's magnetic field in a way that is impossible through direct observation alone. It also provides a measure of the galaxy's overall activity level, the rate at which it is converting the energy of stellar death into the kinetic energy of subatomic particles. The differences we see underscore that a galaxy's energetic output is not just a function of how many stars are born and die, but also of the galaxy's fundamental ability to trap and manage that energy. The cosmic ray anomaly is a testament to the LMC's unique identity, a smaller, more turbulent, and leakier system than our own, whose invisible particle storms reveal the complex interplay between creation and escape on a galactic scale. But beyond the concentrated brilliance of its star clusters and nebulae, the Large Magellanic Cloud is suffused with a far more subtle and pervasive glow. If you could view the galaxy through a filter that reveals a specific wavelength of red light, you would see it not as a collection of distinct points, but as a vast, faintly luminous fog. This is the signature of diffuse ionized gas, a sea of low-density plasma where hydrogen atoms have been stripped of their electrons, causing them to emit a soft, characteristic red light as they recombine. This gas is not confined to star-forming regions. It fills the immense spaces between the stars, creating a tenuous, glowing atmosphere that envelops the entire galactic disk. The existence of this plasma is, in itself, a significant puzzle, because keeping such a vast volume of gas ionized requires a tremendous and continuous supply of energy. And when astronomers tally up the most obvious power sources, the numbers simply do not add up. The conventional explanation points to the galaxy's hottest, most massive stars. These stellar behemoths pour out immense amounts of ultraviolet radiation, photons with enough energy to knock electrons loose from hydrogen atoms. In regions like the Tarantula Nebula, the correlation is perfect. The intense glow of the ionized gas coincides precisely with the locations of these young blue stars. The problem arises when we look at the quieter, more mundane parts of the LMC, far from any major stellar nurseries. Here, the diffuse glow persists, yet searches for the requisite number of hot, young stars to power it come up short. It's as if a large city is found to be brightly lit throughout the night, but an inventory of its power plants reveals only enough capacity to illuminate a few downtown blocks. The rest of the city appears to be shining with no clear source of electricity, presenting a fundamental energy crisis on a galactic scale. This discrepancy has forced scientists to consider more exotic power sources that operate throughout the galaxy. One compelling candidate is the collective output of much older, less obvious stellar populations. While they are not as individually powerful as their massive counterparts, the galaxy contains a vast number of old, hot stars in their final stages of life. White dwarfs, the Earth-sized embers of sun-like stars, can have surface temperatures of over 100,000 degrees when they are newly formed, emitting a significant amount of ionizing radiation. Similarly, the exposed cores of stars that have blown off their outer layers, known as subdwarfs or post-asymptotic giant branch stars, are also incredibly hot. While each one is faint, the combined ultraviolet light from millions of these stellar corpses spread across the galaxy could provide a pervasive background level of ionization, like a multitude of tiny, widely distributed light bulbs collectively illuminating the fog. Another powerful, though less direct, energy source is the turbulent aftermath of stellar death. Supernova remnants do not just fade away quietly. Their expanding shockwaves continue to ripple through the interstellar medium for thousands of years. These shocks can heat the gas to extreme temperatures and generate turbulent motions. This mechanical energy, the sheer chaotic motion of the gas itself, can also contribute to ionization through collisional processes. When atoms and particles collide at high speeds, the impact can be violent enough to knock electrons loose, even without the presence of ultraviolet photons. In the LMC, with its high rate of supernova, the interstellar medium may be continuously stirred and heated by these ongoing shock waves, providing an alternative means of keeping the gas ionized. This would make the diffuse glow not just a product of light, but also a signature of sound, or rather, the kinetic energy of powerful, inaudible waves crashing through the galactic sea. Unraveling this mystery is crucial because the diffuse ionized gas is a major, yet often overlooked, component of a galaxy's ecosystem. It represents a significant reservoir of mass and energy, and its properties influence everything from the pressure of the interstellar medium to the potential for future star formation. By studying its distribution and ionization state in the LMC, where distances are known precisely, astronomers can build better models to understand how energy is transferred and recycled throughout a galaxy. The faint, pervasive red glow is therefore a challenge to our assumptions, forcing us to look beyond the brilliant lights of massive stars and consider the more subtle, collective power of stellar remnants and the lingering violence of ancient explosions that together shape the very atmosphere of a galaxy. Yet the violence that carves out these superbubbles is not purely destructive. It is also a powerful engine of creation. The same shockwaves that hollow out vast cavities in the interstellar medium become the sculptors of the next generation of stars. This is the remarkable process of triggered star formation, a cosmic chain reaction where death gives birth to new life on an epic scale, and the rims of the LMC superbubbles provide some of the most stunning visual evidence of this cycle in action. To understand how this works, picture the expanding shell of a superbubble not as a simple wall, but as a colossal, slow-moving snowplow. As it pushes outward, it doesn't just sweep gas aside. It gathers it up, compressing the diffuse hydrogen that was once spread across light years into a dense, massive layer along its leading edge. This compression is the critical trigger. In the quiet depths of space, a cloud of gas can remain stable for eons, its internal pressure balanced against its own gravity. But when a supernova shockwave slams into it, the balance is violently upset. The external pressure increases dramatically, forcing the cloud to contract. If the compression is strong enough, it can push pockets of gas over the critical threshold where gravity takes over, overwhelming the internal pressure and causing the cloud to collapse irrevocably under its own weight. Within these collapsing knots, temperatures and densities soar until nuclear fusion ignites and a new star is born. The shockwave, born from a stellar catastrophe, has effectively seeded the surrounding space with the conditions necessary for new suns to flare into existence. A breathtaking example of this process can be seen in the supernova remnant known as N49, a tangled web of glowing filaments in the LMC. Here, astronomers have observed young, hot stars and glowing knots of gas that are unmistakably aligned along the outer rim of the expanding remnant. These stellar infants are too young to have formed independently. Their location and age directly implicate the supernova shockwave as their creator. The blast wave from the ancient explosion compressed the pre-existing gas clouds at its periphery, initiating the gravitational collapse that led to their birth. It is a clear case of cosmic cause and effect, with the stellar progeny arranged in a ring that traces the outline of their parents' destructive fury. However, the most compelling evidence for large-scale triggered star formation comes from the intricate structure of the supergiant superbubble DEM L306. This enormous structure is not a single, smooth shell. Its edges are studded with brilliant clusters of young blue stars. These clusters did not form randomly. They are precisely situated in the brightest, densest regions of the bubble's swept-up shell. The sequence of events is like a carefully choreographed dance. First, the winds and supernova from a central cluster of massive stars blow the initial bubble. Then, the expanding shell accumulates more and more material, becoming increasingly massive and unstable. Finally, the shell fragments under its own gravitational attraction, and each fragment collapses to form a new star cluster. In this way, a single, massive stellar nursery can give rise to a second generation of stars at its edges, propagating star formation outward from the epicenter like a wave rippling across a pond. DEM L36 showcases this sequential star formation so clearly that it serves as a textbook illustration of the phenomenon. This process has profound implications for the evolution of entire galaxies. Triggered star formation is a primary mechanism for regulating the pace of stellar birth and for spreading the products of chemical enrichment. The supernova that create the superbubbles forge heavy elements like oxygen, silicon, and iron in their violent hearts. When the bubble expands and triggers new star formation, these newly minted elements are incorporated into the next generation of stars and planets. This means that the planets forming around stars in these triggered clusters may be richer in the elements necessary for rocky worlds and perhaps even life, compared to planets born from more pristine gas. The process creates a self-propagating cycle. Stars are born, they live, they die in explosions that create bubbles, and those bubbles trigger the birth of more stars. It is a feedback loop that ensures a galaxy does not consume its gas supply in one frantic burst, but instead spreads star formation out over space and time, allowing for a more sustained and complex evolution. The superbubbles of the Large Magellanic Cloud are therefore not just empty cavities. They are the active, vibrant frontiers where the galaxy's future is being written, one collapsing cloud at a time. Yet all the individual mysteries we have explored, from the ghost of supernova 1987 to the warped bar and the anomalous cosmic rays, converge into a single, overarching story written not in light or motion, but in the very chemical DNA of the galaxy's stars. This is the grand narrative of the Large Magellanic Cloud's chemical evolution, a history that reveals why this galaxy is fundamentally different from our own Milky Way. When astronomers analyze the light from stars in the LMC, they find a consistent and telling signature: the overall abundance of elements heavier than hydrogen and helium, what they call metals, is significantly lower than in similar stars within our galaxy. Our Sun, for instance, has a metal content about 2 to 3 times higher than the average star of comparable age in the LMC. This difference is not a minor detail. It is a profound clue that the two galaxies have lived very different lives, following divergent evolutionary paths over billions of years. The level of metal enrichment in a galaxy is essentially a measure of its industrial activity across cosmic time. Heavier elements are not produced in the Big Bang. They are forged in the nuclear furnaces of stars and then scattered into space when those stars die, either in gentle planetary nebula ejections or in violent supernova explosions. This newly enriched gas then mixes with the pristine hydrogen and helium of the interstellar medium, becoming the raw material for the next generation of stars. Each successive generation is therefore born with a higher metal content than the last, A galaxy that has undergone rapid, intense cycles of star formation will quickly become metal-rich. A galaxy that has formed stars more slowly and sporadically will remain more pristine. The LMC's lower metallicity is a direct indicator that its star-forming history has been more hesitant, more punctuated by long quiet periods, compared to the relatively continuous and vigorous activity within the larger Milky Way. Several key factors, each tied to the phenomena we have discussed, conspired to create this slower chemical evolution. First, the LMC's smaller mass played a decisive role. With less gravitational pull, it has a weaker grip on its own gaseous resources. When massive stars exploded as supernova, the energy of these blasts was more effective at heating the surrounding gas and even ejecting it entirely from the galaxy, a process known as galactic winds. This means that a significant portion of the newly forged heavy elements were not recycled into new stars within the LMC, but were instead lost to the intergalactic void, slowing the pace of its chemical self-enrichment. Furthermore, the galaxy's lower mass meant it started with a smaller initial reservoir of gas, so its star-forming fuel tank was simply smaller to begin with, limiting the scale of its early industrial output. The second major factor is the galaxy's dynamic interaction history. The gravitational tug-of-war with the Milky Way and the repeated close encounters with the small Magellanic Cloud did not just warp the LMC's disk, they profoundly disrupted its gas content. As we saw with the Magellanic Stream, these interactions have been stripping gas from the LMC for billions of years. This removed potential fuel for future star formation. However, these same interactions also had a paradoxical effect. They periodically funneled gas inward, compressing it and triggering the intense but short-lived bursts of star formation we see recorded in the split red giant branch and the lopsided distribution of young clusters. This created a staccato rhythm of chemical enrichment, intense, metal-producing bursts followed by long quiescent periods, rather than the steady, continuous production line we believe operated in the Milky Way. The chemical fingerprint of the LMC is therefore not one of smooth progression, but of fits and starts, a record of a galaxy whose evolution has been repeatedly jolted by its gravitational relationships. The types of supernova that have dominated the LMC's history also leave a distinct chemical mark. Core collapse supernova from massive stars produce and distribute elements like oxygen, neon, and silicon. Thermonuclear supernova, which occur when white dwarfs explode, are the primary cosmic source of iron. The ratio of these elements in a galaxy's stars tells scientists about the relative importance of these different explosion mechanisms over time. In the LMC, some studies suggest a slightly different ratio of alpha elements like oxygen to iron compared to the Milky Way. This could indicate that the early chemical enrichment of the LMC was dominated by massive stars, with thermonuclear supernova becoming more significant later in its history. This pattern aligns with the idea of episodic star formation, where a burst of massive star birth and death would flood the galaxy with alpha elements, followed by a period where the slower evolving lower mass stars would eventually contribute their iron-rich ashes. Ultimately, the chemical composition of the Large Magellanic Cloud is its autobiography. Each element ratio, each metallicity measurement, is a sentence in a story that recounts its birth from pristine gas, its struggles to hold onto its resources, the disruptive influence of its powerful neighbors, and the brilliant, violent lives and deaths of its stars. This unique chemical fingerprint makes the LMC far more than just a nearby galaxy. It is a critical control sample for understanding galactic evolution as a whole. By comparing its chemical history with that of the Milky Way, astronomers can isolate how factors like galaxy mass, environment, and interaction history shape a galaxy's destiny. The LMC's relative lack of heavy metals is not a sign of insignificance, but a badge of its unique identity, a testament to a life lived on a different, more turbulent track than our own galactic home. This journey through the strange phenomena of the Large Magellanic Cloud has taken us from ghostly supernova remnants to rogue black holes, from distorted structures to anomalous particles. Every mystery we have uncovered paints a picture of a dynamic, evolving system, a galaxy with a vibrant past and a turbulent present. But all of these individual stories are merely chapters in a much grander narrative, one that points toward a single, inevitable, and spectacular conclusion. The most profound destiny of our galactic neighbor is not to remain a separate entity, but to become one with our own Milky Way in a collision of cosmic proportions. Current measurements of the LMC's motion reveal a startling truth. It is not merely orbiting the Milky Way in a stable, distant loop. Instead, its trajectory is carrying it directly toward us on a decaying orbit. Sophisticated simulations predict that in approximately 2.5 billion years, the two galaxies will begin a slow, gravitational dance that will culminate in a full merger. This timescale is vast from a human perspective, but it is a mere moment in the life of a galaxy. The serene companion we see today is, in fact, on a direct collision course with its giant host. The initial stages of this merger will be a spectacle of cosmic destruction and creation. As the LMC swings closer, the Milky Way's tidal forces, which have already warped its disk, will become overwhelmingly powerful. The smaller galaxy will be stretched and shredded, its spiral structure dissolving into great streams of stars and gas that will be pulled out into long, luminous tidal tails arcing across the sky. Within the LMC itself, the increased gravitational compression will trigger a final, ferocious burst of star formation. The remaining reservoirs of gas will collapse in a blaze of glory, igniting millions of new stars in a starburst so intense it will briefly outshine the combined light of the galaxy's previous history. This will be the LMC's last magnificent act, a final bloom before its identity is erased. For our own galaxy, the impact will be equally transformative, though less destructive. The influx of billions of new stars from the LMC will significantly alter the Milky Way's architecture. The relatively thin disk we know today will be puffed up and thickened, gaining a more chaotic, elliptical-like structure. Our night sky, as seen from a future Earth, would become unrecognizable. The familiar band of the Milky Way would be joined by brilliant, new streams of light, the dissolving corpse of the Large Magellanic Cloud, creating a celestial tapestry of unparalleled complexity. Crucially, this merger will deliver a massive infusion of fresh, relatively pristine gas into the Milky Way, reigniting star formation in our galaxy's core and potentially giving rise to a new, bright galactic nucleus. This event will also solve one of the greatest lingering mysteries, the fate of the LMC's dark matter halo. During the merger, the invisible halo surrounding the smaller galaxy will be stripped away and assimilated into the much larger halo of the Milky Way. The gravitational wake we see today is just a preview of this ultimate dissolution. The merger will provide astronomers of the far future, or whatever intelligence exists then, with a direct laboratory to study how dark matter behaves during such a colossal interaction, potentially revealing its true nature. The impending collision underscores a fundamental truth of our cosmic environment. Solitude is an illusion. Galaxies are not isolated islands. They grow and evolve through a hierarchical process of merging and accretion. The eventual assimilation of the Large Magellanic Cloud is not a rare catastrophe but a standard part of galactic life. In fact, our Milky Way itself was built through similar events, having consumed numerous smaller dwarf galaxies over its long history. The LMC is simply the next and largest meal on the menu. This fate ties together every strange phenomenon we have explored. The warped bar, the lopsided star formation, the anomalous chemical evolution. All of these are symptoms of a galaxy living under the relentless gravitational influence of its future destroyer. The 30 strange phenomena are not isolated curiosities. They are the signs of a system in motion, a galaxy responding to the pull of its ultimate destiny. The silent, seemingly static sky is a deception. It is a snapshot of a slow-motion ballet that will end in a magnificent embrace, forever changing the galaxy we call home. And so, our journey through 30 of the most profound mysteries of the Large Magellanic Cloud draws to a close, not with a final answer, but with a deeper appreciation for the questions themselves. We began with the ghostly silence where a neutron star should be and ventured through stellar nurseries of unimaginable scale, past invisible giants of dark matter, and into the heart of a galaxy seemingly missing its central black hole. We have witnessed stars being devoured, others being flung into the void, and entire galactic structures bent and twisted by gravitational forces. Each phenomenon, from the intricate shells of planetary nebulae to the faint glow of decaying dark matter, has revealed a layer of complexity that transforms our closest galactic neighbor from a passive smudge of light into a vibrant, dynamic, and deeply individual cosmic entity. This exploration underscores a fundamental truth that rewrites our understanding of cosmic hierarchies. The Large Magellanic Cloud is not merely a simple satellite, a celestial backwater orbiting our grander Milky Way. It is a galaxy in its own right, with a rich and turbulent history, a unique chemical identity, and an internal engine of creation and destruction that operates with its own distinct rhythm. Its smaller size and irregular shape are not signs of insignificance, but of a different evolutionary path, one shaped by isolation, interaction, and a series of cosmic events that have left their marks in the motions of its stars and the composition of its gas. It serves as a crucial control sample in the study of galaxy evolution, proving that the universe's most fascinating processes are not exclusive to grand spiral galaxies. They are happening right next door on a scale that allows us to observe them with unparalleled clarity. The true value of these 30 mysteries lies not in any single solution, but in their collective power to propel scientific discovery forward. Each anomaly is a crack in the facade of our current understanding, an invitation to question, to theorize, and to look deeper. The missing compact object of Supernova 1987 forces us to refine our models of stellar death. The warped bar and lopsided star formation provide a real-time laboratory for studying galactic interactions. The hunt for a runaway black hole and the search for the source of the gamma-ray bubbles test the limits of our gravitational theories. It is this relentless confrontation with the unexplained that drives innovation in our telescopes, our simulations, and our fundamental concepts of physics. The Large Magellanic Cloud, in all its strange glory, is a perpetual catalyst for curiosity, ensuring that our map of the universe is never truly complete. This cosmic story is not locked away in distant data. It is written across a corner of the sky that is visible to the naked eye. For those fortunate enough to live in or travel to the southern hemisphere, the Large Magellanic Cloud hangs in the darkness as a permanent celestial wonder. The next time you find yourself under a clear, dark sky far from city lights, take a moment to look toward the constellations of Dorado or Mensa. There you will see it, a faint, wispy cloud that is so much more than it appears. It is a gateway to the mysteries we have explored, a reminder that the universe is a living, changing, and deeply mysterious place. As you gaze at that soft glow, consider the violent stellar factories, the invisible gravitational tides, and the silent, ancient stars it contains. We would love to hear which of these 30 phenomena captured your imagination most profoundly. Was it the sheer scale of the Tarantula Nebula, the detective story of the Hypervelocity star, or the mind-bending possibility of a Thorn-Zitkow object? Share your thoughts in the comments below and continue the conversation about our incredible cosmic neighbor. The pursuit of understanding is a shared human endeavor, and every new perspective brings us closer to unraveling the secrets of the cosmos.